Hi, everybody. Oh. Just 1 second here. Okay. A little background music for everybody. Thank you, everyone, for being here for this discussion on artificial intelligence, and more specifically, artificial intelligence in the realm of particle physics, as you've just seen in the film here. I want to also give a big thanks, actually, to everyone who's joining us online on this little thing called the World Wide Web, which, you're welcome, was invented here at CERN, actually. So welcome to everybody who's online on our live stream joining us. Thank you for staying after the film, everybody who's in the room. We're going to have an interesting discussion today with 4 of our colleagues from the film that you just saw. So I'm going to invite them up one by one. First is the filmmaker, Matteo Benedetti. If you could come on stage. Congratulations, Matteo. You can have a seat, yeah. And then our very own researcher, Maurizio Pierini from CMS, who's occupied with his little one. Good to see you both. And last but not least, we have Katya I'm going to try to pronounce this correctly. Sorry, Katya. Govorkova, who's also a researcher here with CMS. You can figure out where they all met. And then we also have on Zoom, I hope, Jennifer Nyaduba. Maybe. Probably. Anyway, I think she'll join us in just a second. So we'll move on for the moment. And what we're going to do is, rather than give you long-winded introductions for everybody here, I'm going to ask everybody actually to just introduce themselves. And we'll start with Matteo. Give a little background. Tell us about where you came from and how you ended up here.
Okay, I'm just from Rome. I'm a TV producer, and I work in I usually work in very entertainment TV shows. But that one was one project that I wanted to realize by myself as an independent project. So I contacted different companies, and then I met with the Sprixar company, which is a production company in Rome, and they liked the idea, and we basically produced this documentary that was designed to inspire young audiences. So it's very rock and roll documentary about a science story. And now our partner, which is Canadian and is in charge of distribution of the product of this project, is negotiating different contracts with different broadcasters. Actually, in France, is going to be on rotation on Science and V, which is a thematic science channel available on Canal Plus and other platforms. And in Italy, is going to be aired on November on Rai Play, which is the main public broadcaster in Italy, hopefully in November. And other territories are coming.
Okay, thanks, Matteo. Maurizio.
Maurizio Pierini, I'm a researcher. I mean, you heard the story during the movie of how I got here. I don't know what to say more than that, in the sense it was extensively covered. But I mean, I can tell you what happened since the movie. I've been appointed as head of AI on the research sector at CERN. I'm now covering the entire AI in the experimental physics, theoretical physics, and IT departments, and as part of the new CERN AI strategy. It's been interesting. We're putting together the next big steps beyond this one. And yeah, it's working. We're happy.
Katya.
Yes, so yeah, I'm Katya. I'm a physicist. I've been doing data analysis for the last 12 years at CERN. And yeah, I guess the documentary explained well what we were doing. And maybe lately I can say that I'm still with MIT, but I switched experiments. I'm working in LHCb experiment. And also I'm looking for new type of astrophysical objects at LIGO. It's another experiment that is in the US. So this is also taking part of my time now.
Great. And do we have Jennifer on Zoom? I think not. Okay. So hopefully she will join us at some point coming up. And if not, I guess that's the way the internet breaks, isn't it? So I wanted to actually start quickly, Maurizio, with you. And when people hear about AI, of course, what they think about today is Gemini, ChatGPT, all of these different large language models, which are, of course, one type of AI, but not the only type, and really not, for the most part, the type that we use here. So could you just give us a little primer for the audience on how AI and what types of AI are used specifically at CERN?
So what we do since, we use machine learning, which is the big branch of classic kind of algorithms that started with neural networks that got into something else. Now it's back with these neural networks since the 90s at CERN. What we typically use them for is pattern recognition in our large data sets. The kind of stuff that you heard about, classification, so jet tagging, and so on. This is different than what ChatGPT and Gemini do, which is language processing. Our data are not clearly text, but it is. Ultimately, it's at the end, it's really the same in the sense you have some data set and you are looking for patterns, and machine learning is very good with patterns. So traditionally, the things that we've been doing is asking questions like which kind of particle is this, or how much energy it carries. These are called classification regressions. With this project that you saw in the movie, we started going towards unsupervised techniques, and this is now taking over. It's actually, now it's pretty much hot topic, live stream. Other experiments are doing this, and we're trying to bring it to the next level. And this is one way in which we're looking into empowering physicists at CERN with new tools, breakthrough tools that could facilitate discoveries. And now we're looking into agentic AI, so Claude mostly now, to try to basically go through this process and see if this new technological breakthrough could open up new perspectives for our research. So I like to quote a lot. In the last 2-3 years, I do this basically every time I speak. Freeman Dyson, who was a very successful physicist in the last century. He was one of the fathers of the Standard Model and of the quantum field theory. And he used to say that every scientific resolution, if you look at it, it didn't really start with a conceptual breakthrough. It started with a technological breakthrough. From the invention of the telescope to the invention of the accelerators, there is a technological breakthrough behind. And even for deep learning and for AI, this is the same, because people like to put 2012 when the first computing vision was demonstrated with deep learning, but the same year there was another paper that demonstrated that you could actually train these things on graphic cards for gaming. And this was the technological breakthrough that allowed for the other things to happen. There is always a technological breakthrough that opens up a new horizon. We are thinking at this as our new technological breakthrough, and hopefully this will facilitate a discovery in the years to come.
This is a bit how we justify fundamental research as well. The idea that we don't really know exactly what we're looking for, but if you don't find the new ideas, if you don't find the new theories and the new understandings of nature, then you don't manage to commercialize them, exploit them, you know, in the way that that people expect to get return on their investment. You know, so obviously it's interesting. You know, no one would ever propose to make GPUs, for example, to aid, you know, particle physics. They would make GPUs, you know, for gaming, obviously, right? And so it's the same, basically the same logic, you know, that we use, the sort of the backwards logic in a way that works there. So I wanted to turn to Matteo now. This film is one of the most, I would say, complete sort of 360 treatments of what we do here, actually, that I've maybe even ever seen, because you really go into, you know, a lot of the physics, you go into all of the technology at some level. I mean, you don't go deep into a lot of it, of course, because you only have 68 minutes or whatever it is, but you do treat basically, you know, kind of everything that we do here from every perspective. Even though ostensibly the film is about, you know, is about AI, and I understand that's the background and everything, but you mentioned that you wanted to approach, you know, you wanted to be able to get in contact with and to speak to young people, you know, and how did, you know, the incorporation of, you know, this breadth of information, which is quite varied, you know, and quite deep in many ways, this information with your goal to reach young people, you know, how did you reconcile those two things? Because it's not necessarily obvious that you can include so much information and obviously speak to young people as well.
Well, I think, I mean, what I've realized that is young audience have a span of attention which is really, really low. So I have to keep up the rhythm in the first 15 minutes. And that's why it's so dense as documentary. And then the other idea is that, the other idea is that usually this kind of documentary has the narrator is a really enthusiastic journalist that talk about science to the audience. So I figured, we thought with the director, why don't we do a narrator which is depressed and which is nobody, so that maybe the audience could feel something in common with that, because you know when you make a character that has no face, you think that maybe the audience could see himself somehow. That was the idea, and the reason why I wanted to talk about even history of CERN and even how researchers work together is because I found that in the market there's a huge demand of science product by general audience, but I wanted to actually make a kind of unique product where you have a rock and roll narrator, which is depressed, where you have all general information about a beautiful place that this is, where in a time where we are full of conflicts and where the logic go away, this is a place where all the world come together to work together. And I wanted to make the young audience know that, because they don't know that. I mean, even if, of course, you're doing wonderful jobs in communicate the CERN brand, I think we must do. I mean, there's space, there's room for many different kind of stories about CERN. That's why I wrote at the beginning that this is just one of the thousands of stories that you can find here.
Thanks. Katya, I wanted to, so you've been doing, you said data analysis for CMS for 12 years, is that right?
For CERN, but I was mostly LHCb.
Okay,
actually.
okay.
But yeah.
So another one of the experiments for those who might not know. But and so ostensibly you've been doing data analysis and physics since before the development of you know AI algorithms or AI assisted algorithms, and now you're working on them. So what for you has been the biggest shift in the way that you look at the process of data analysis in this huge context?
Yeah, it's a good question. I guess I had to learn a new career path, which is being a machine learning researcher and not a physicist, or like in parallel, which is a bit complicated because you have a main job and you have to learn something on a side, right? So by looking at the courses online and everything, you see what is the approach there, but then you'll get surprised how similar it is, because the research is research, and the scientific method that Maurizio explained in a documentary is the same for machine learning and for physics. But then, yeah, you have to learn all the new methods and keep up with them, which is really complicated because every day, I don't know, there is thousands new papers on a new cool machine learning stuff, so you need to learn to filter what is important for your problem, what is not. Yeah, I think in the end, physics research is still like physics oriented, even then you use machine learning. But I transformed to machine learning researcher during this process, and now I'm moving towards this out of physics, actually. Yeah.
And so did you, so you mentioned, so you basically were doing essentially like those courses that you get served like on YouTube about like, hey, learn how to use AI, whatever kind of thing. I mean, obviously, I'm sure your level is higher than what a lot of us are getting served up. But I mean, that kind of thing, you were doing it on your own, basically, like that.
Yeah. But there is also a lot of online resources available from top universities in US, for example, like Stanford. They'll put online their actual courses on machine learning, and you can follow them, which is a very high level of research. So you can do that as well.
Okay. So I want to get into a question, actually, which, I mean, for me is the most interesting part of AI. And obviously, probably the sort of the most controversial part as well. At the end of the film, I think you close, Maurizio, with the statement that you're trying to replace your colleagues, your theorist colleagues, with AI, right? And I know that's a bit tongue-in-cheek, but at the same time, of course, it's really not tongue-in-cheek. I mean, in some sense, you mean that, right? And so I wanted to start discussing a little bit about, well, first of all, how plausible is that? First, number one, but secondly, I want to talk about what it means for us to understand the science that we are discovering. Okay, and if we're capable of creating algorithms that at some point are capable of understanding, in quotes, that science, does it matter if we don't? But let's take that as a second question. So I think the first question for you, Maurizio, is there a realistic prospect in the near term that you could actually replace your theorist friends with AI in the context of at least, what we're doing here?
I mean, the point is that, so a theorist, in the relation between the theorist and the experimentalist, there are two aspects. There is always, I mean, the last 30 years, the process was a theorist suggests an experimentalist an experiment to do, the experimentalist does the experiment and then goes back to the theorist to interpret the outcome. So this is the part that I'm trying to get rid of is the first. The sense, nature, she suggests me the experiment to do. I do the experiment, and the theorist, from the outcome of the experiment, his job is to create the next theory. So the first part has been guiding us in the last 40 years, because once you write down the equation of the standard model, you say, okay, so you should be seeing this, you should be seeing that, and we have done that part. Now we are run out of, every theorist has their own idea of how we should go next, and there is no real reason why we should go there or there, and maybe we should just go there. And this is what we're asking the algorithm to do for us, looking at what the LHC produces. The part that, at least when we shot the movie, was science fiction, was to replace the theories in the second aspect, which is the data come, and then from there you need to formulate the next theory. But this is what the big companies are trying to do. Anthropic, for instance, is really trying hard to create the next Einstein synthetically. and not by chance their chief scientific officer is a particle physicist, is a theorist. He's trying to replace himself. So it's not really a replacement in the sense. I have no sense of the fact that even if you develop artificial general intelligence, that this thing would care about how the universe started and so. This is very human. So the way I see all these tools is that they are tools. So they are not going to replace, the idea is not to replace the theorist in absolute, is to make the theorist focus on the second part of the work, while nature should do the first part of the work, which give me suggestion. And in this second part of the work, the idea is to empower her or him with tools that go beyond our capability. Once I saw a short documentary, 15 minutes, in which a colleague from Paris used to say that the crisis in which we live in energy physics, the fact that we don't know what's next beyond the Higgs boson, could be a limitation of our intelligence. So the argument was a dog would never come out with general relativity. Maybe we are dogs when confronting to the problem we have. And maybe AI could be a way to expand our mind beyond our biological limitation and give us the solution to all of this.
I mean, this would be akin to, like you say, developing telescopes and then inventing astronomy, because you can actually gather data. So it'd be augmenting our technical capabilities, but essentially augmenting our intellectual capabilities rather than just our abilities to perceive and to take data. So you want to essentially envision the role of the theorist as sort of in the inverse order. So rather than being one of the things I think anybody who's watched, for example, Particle Fever, or quite a few of the other documentaries that have been made about particle physics, one of the central tenets of these films is that actually particle physics is a quite creative discipline in a sense, because these theorists, like you say, have to essentially just come up with ideas, test those in the mathematics, and then if they look feasible in the mathematics, then actually build machines that can test them experimentally. And so this notion of it being creative, right? If you eliminate the quote, I don't want to say eliminate. If you displace maybe the creative part, right? And a machine does it, then how does that change the balance in the field?
I don't know. I mean, to me, it's still the work the job they would end up doing is the same, except that it would be more data driven. They would start from facts and not from pure mathematics. The mathematics always there, because effectively all the problems that we have in energy physics, you can bring them down to a very mathematical fact in the theory. So, and then use creativity to go beyond that. But our task as experimentalists is to guide the process, saying, this is what we see, this is what we don't see. This is how they used to work, like 3 or 4 generations of theorists ago, when the standard model was not such a clear picture. It was all about new experiments. People were just doing experiments, testing everything that they could do. There were a lot of small experiments doing any sort of measurements. And these measurements were feeding the theory community that then was coming out with ideas. And this is how the standard model was created. So this is not really, we're not trying, my point is that the idea is not to change things, it's to maybe to go back to the pre-big data way we used to work. And to give you an example, there is a fantastic book which is called Noble Dreams, which tells the story of the UA1 collaboration at CERN after they discovered the W boson, and they received the Nobel Prize for that, the spokesperson, Carlo Rubbia, with the guy that made the accelerator possible, which was Vandermeer. So at some point, they start to see these weird events, and they couldn't figure out what they were. And what they did is that they printed on slides the images of these events. So what they were seeing in the detector, and they couldn't really understand what they were. And then they were going around here saying, what could this be? And someone said, you might be seeing dark matter production. And this was cool. And they were thinking they were after a new discovery. And then it ended up being something else. But everything started with 5 events that they couldn't make sense of. 5 anomalies. So the point is that we have stopped working this way because we are so much overwhelmed of data. So we don't look at the data anymore one by one because there are just too many. And of predictions to verify that we just changed the way we worked. I think that at this moment of crisis where we don't really know what's the next direction, we should go back to that way of doing things. And this is basically what we're trying to do, but AI-powered.
Okay, I like that. Looking at it that way, that's a much more palatable vision, I think, of using AI than a lot of what we see in the media. Matteo, so you in the film, you are the anxious, narrator, right? Who is somehow soothed, by the passion and the dedication of these physicists, right, that you're following, and I think in a larger context, the pursuit, right, itself. And in the end, you say that makes me feel good, right? But what exactly is it that makes you feel good about that? Like, what's the
idea? That character is not me. We don't know who that is. It's a character. And it's a secret. And that character actually was depressed. I mean, the idea was he was depressed and he was lost himself. He's a character that has lost himself, and maybe he can find himself again by learning new stuff. So the learning process, which is living, telling this story, help him feel better and find himself again. That's the idea.
But what is it about knowing that there are this group of people that are facing all of these challenges and standing up to them continually and continuing to go forward? What about that is to you? I think palliative about that.
He is understanding gradually, and the small lesson that he takes from their story, sometimes he tells to the audience. For example, never stop asking right questions. I mean, instead of looking for answers, one thing that make him feel better is that maybe he could change the perspective, and maybe it's not the answer, it's the questions. And that's it.
So when you started this project, how many years ago did you start the project actually?
2 years,
2 years ago.
23 and 24.
Okay, so 3 years ago when you started the project, how much of this physics and how much about CERN did you actually know at that time? I mean, were you a CERNophile or?
I've always been passionate about physics. I always thought that is the hard science that go very deep, and they search for, the most important thing that we don't know in the universe, which actually I don't know what it is, but I feel that is the core. And so I've always been passionate about that. And at that time, it was just, I wanted to do something by myself, and I've been knowing him we are old friends, and I just asked him if I know that he was working here at CERN, so he could be a good source of stories. And so I just asked him, listen, I want to do some science documentary. If you have good stories, please tell me. And it takes a while because he came back to me after months And as I said before, he invited me over his home, and we spent like an afternoon, and he talks like a river. And I was pretending to understand everything, but I was recording with my phone so that I can listen the transcription day after. And when I see the story of researchers that were going together gradually, one by one, focusing on problem and then increasing the solution problem after problem, I thought that could be a good story for a curious young audience that would could have the experience of see how is the life of a researcher at CERN. And that's why I choose to tell this story.
And I find it interesting, the focus on young people. So, like, was that a personal interest? I mean, did you say when you started this, like, I want this to speak to young people because I think this is important, you know, or was that a practical consideration, as in, you know, there's a space in the media landscape for this kind of content, you know?
At the beginning, I wanted to be, it was like in the market, as I told you before, I think all the science documentaries are pretty institutional, pretty, you know, classic. And I wanted to do I wanted to make a story of a group of researchers seen as a gang of adventurers, of people who are human beings with problems, with emotions, with even, you know, at the beginning, Jennifer says, at the beginning it was really difficult to work here. I mean, they made confessions about even the first difficulties that they find when they are entering this environment. So I wanted to give nuances of these characters. I wanted the audience focus not only on the technical problem, and I even go deep on the problems because the project goes very fast at the beginning with general information about everything, and then about the characters, the protagonists, and then deep in the problem with all the problems and successes that they get along their work. And I don't know if I made it. I mean, only the audience will say that. Hopefully, I will receive feedback from audience here right now and wherever I will be talking about this project.
You'll actually have the chance to get some feedback from people directly. I'll explain in a few minutes, but coming up. So we have about 10 more minutes left, and so let's turn to the future. Okay, so Katya, what is the future in AI at CMS, for example, in general, and I mean in the sort of near term, you know, like things that you're actually working on right now that will be exploitable in the, you know, the really near future, and what's the sort of the dream, you know, in 5 years or 7 years. 7 years is like 3 generations, I guess, or 8 generations in AI speak, but.
I think it's really hard to imagine what's going to be even in 1 year because things are changing so fast. And I can give you an example. I was in a agentic AI workshop at ETH at Zurich, and there was a very nice presentation. It's open source. Maybe I can share the information somehow, but basically the person was imagining how the physics research will look like in 2-3 years, and it completely blew my mind because with agentic AI it would just be completely different. You don't go and look at the data set with hands, you don't program anymore anything yourself. You basically get the chance to be more creative, actually, the previous discussions that you had, because the technical part is kind of outsourced to AI, and you get to think, what is the next hypothesis I want to test? What is the next thing I want to test? And then maybe like you talk I guess many of you talk with a ChatGPT on daily, but you talk on a specific LLM that is designed for physics about your hypothesis, and then maybe there's an automatic AI system that tests this hypothesis on the data, and then it's more about you become a deep thinker rather than a person that has to program everything, and like, yeah, it's very different, and I cannot fully imagine how it's going to be, but I think it's going to be very exciting.
So you can actually imagine that in 9 months or a year or something like that, you will no longer be coding anything, basically? Is that possible?
I would say it is possible on some level, but I don't know, maybe Maurizio has other ideas about that. I see that it could be possible, yes.
Is that to you, is that a good thing? I mean, do you, if you never write another line of code, will you say, this is great, now I can be creative, I can just come up with ideas to test and stuff like that? Or, is there a little nostalgia for actually having your, hands in the engine compartment?
I think it's a good and a bad thing, and as always with great power comes great responsibility. So in this talk that I mentioned in Zurich, the guy was showing the example of future PhD students using this AI tool where you don't need to code, you don't need to do anything by hand, and one potential future PhD student learned nothing through his PhD, basically. Because you don't learn how to think if you have everything automated. But then he showed another example of another potential PhD student in the future using the system to learn how to think and how to do research properly. So I think we have a great tool in our hands, but we need to learn and adapt how do we use it to our advantage.
Yeah, Mauricio.
So this, I think, is... So very recently, I found myself in giving talks to students to tell them, to warn them that this is going to be extremely hard for them. Because basically, the equation of research used to be student plus supervisor equals result, where the supervisor comes with a lot of experience and little time. The student comes with not so much experience, a lot of time. The exchange, the chemistry, creates a process in which the students not only learn from the experienced supervisor, but also produce original results with that kind of guidance. Now the equation is student plus supervisor plus AI tool equals the result. So what can happen is that there can be the very passive student, supervisor says, oh, it would be interesting to look at that. Student go back to the office, open Claude, ask the question to Claude, take the answer, and bring it to the supervisor. Student costs, now I'm getting into money, which sounds dirty, but at the end, this is what it is. Student cost in Switzerland, 4,000 Swiss francs a month. Claude costs 20. 100 if you want to go the superpower. In the equation, the student cannot just be the link between the supervisor and Claude, because the supervisor can use Claude. The students needs to change the work towards being Claude's supervisor. And this is complicated, which means that during the PhD, the students needs to grow its intuition of the physics, because Claude, I can tell you, makes a lot of mistakes. Any of these tools make a lot of mistakes. You need to be quick in identifying them before it goes to the tangent. And this is the way you should be using. You should leverage, I leverage experience when I basically talk to Claude the way I would talk to a student who is not particularly bright, but very technically skilled. Now the question is, we need to grow a generation of students who are not necessarily technically skilled, but extremely bright in the physics intuition. So physics overview, physics intuition. Now what I'm worried about is that in the last 20 years, so since I left university, it seems to me that the trend went actually in the opposite direction. We trend to creates generations of students more and more specialized in technical skills, and the physics was put a little bit on the side because the number of hours you can teach a student in a week is fixed. So if I have to put a C++ course, if I have to put an AI course, if I have to put a Python course, where do I take the hours from? I got the physics. So for instance, experimental physicists takes less theoretical physics classes than in the past. Now, these tools come in, and actually should have been the other way around. You should have trained basically everyone sort of as a theorist, and then specialized afterwards. So I think that the next 5 years are going to be extremely challenged because the university's curricula needs to stay focused on the big picture and on the basis. And the students in their PhD would be called to something extremely difficult, which is make yourself in the equation not dispensable. And so what's going to happen is going to happen that we see that science is cut, we have less and less money, which means less and less PhD students. Our PhD students will be asked to have 2, 3, 4 projects in parallel with 4 AI agents in the back. So the students will be asked to be a professor. And this is going to be challenging.
Yeah, not having gone through that process, it's not obvious how to get there. Yeah, that merits a lot more discussion, but we don't have time now. We only have a couple more minutes. So, Matteo, I'm going to leave it with you to finish up. So, can you tell us what's next for the film, and also what's next for you? If you have another project on science or something like that in the future, what's your...
I'm actually working on some projects, but completely different issues, subjects, sorry. This documentary is going to be in France starting on September 9 on Science AV, which is a thematic science channel on Canal Plus and other platform. And in Italy is going to be available on November, hopefully on Rai Play. We're actually negotiating, so the deal is not closed, but we're negotiating. They're interested. And there's other negotiations with territories in Latin America. So, but we don't have the news already. So there's our partner which is working on that.
Great. Well, thank you everyone for being here. Thank you to Matteo Benedetti,
Thank
Maurizio
you.
Perini,
Thank you.
and Katia Govorkova. Sorry about that. Jennifer didn't manage to join us, as you can see, so unfortunately we didn't get to speak with her. But if you found that interesting and you would like to ask questions, we are now heading over to the globe, which is the big ball, basically that way, and the big wooden ball, and we're going to be in the globe for half an hour between 6:30 and 7, and you can come and ask questions and have the ability to interact on a more one-to-one, let's say, level with our guests here. And so that will be in about 15 minutes. We'll start, I mean, we're just going to basically head over there. So if you're interested, please join us. And we have a whole bunch of other stuff going on. But I actually don't have the slide. No, sorry. Session 2 at 6:30 here is Space, Ocean, and the Thirst for the Unknown. Not the first. So anyway, thank you again for staying. Thanks to our audience online for watching us on the web. And we will head over to the globe. And so please join us if you have other questions or you'd like to get into any deeper discussion about any of the subjects that we spoke about now. And I hope you enjoy the rest of your evening here at CERN. So thanks, everybody. Thanks to our panelists.
Alors, 1, 2, 1, 2, 3, essai, 1, 1, 1, 2, 3, 4, essai, et, 1, 2, 3, 1, 2, 3, 1, 2, 3.
Donc chez elle, ça va, mais chez moi, non.
Essayez. Pardon. Oh là, j'ai mal avec lui. Oui, j'ai toujours mon micro. 1, 2, 3, 1, 2, 3, 4, essai, 1, 2, 1, 1, 2, 3. 1, 2, 3, 4, essai. 1, 2, 3, 4, 5, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, essai, 1, 2. 1, 2, 3, 4, 5, essai, 1, 2. Ça vous va? C'est bon? Ok. Non.
What is this? Whoa. I am Fernão de Magalhães, Portuguese explorer and aristocrat. I sailed from the port of Barrameda de Sanlúcar, the 20th of September of the year of our Lord, 1519. I sailed towards South America, looking for a passage to las Islas de las Especias, and trying to fix my beard. The Spice Islands, I know this passage exists, but I don't know. My astronomical observations, my calculations, my charts, I must have done some mistake. And I don't know, where is my ship? Where's my crew? Whoa, what is this vessel in here? I've never seen anything like this. Oh, remarkable. And where are you? Where am I? Do you have a flag?
Welcome to the 21st century,
21st
Ferdinando de
century.
Magalhães. Come with me.
So, I'm now in the future?
Indeed, you have traveled into the future. You are at CERN.
At CERN, I don't know what that is, but that's remarkable. What is this strange vessel that is in here? I don't recognize it.
It's a sort of time machine.
A time machine. Oh, okay, so that explains it. That must have been the ship that carried me here then.
Not quite. It doesn't bring us into the future, but it takes us back in time.
Back in time. So, you know, I crossed oceans, you know, I discovered new worlds. I charted the unknown.
That's not so different from what this machine does. It lets us journey back to the origin of the universe 14 billion years ago by recreating conditions that existed just after the Big Bang. We explore territories that no human has ever witnessed directly.
So you are explorers, but you don't sail across oceans.
But across time, matter, and the laws of nature, we push into the unknown just as explorers like you crossed new seas. And just as today others venture into the depths of the oceans and to space.
I see. So your maps are different, but the spirit remains the same.
Exactly. Every generation has their own frontiers. Yours lay beyond the horizon. Ours lie in the infinitely small, the infinitely vast, and questions that has not been answered and even asked yet.
So you're curious people, huh? Curiosity always demanded courage. Mine brought me to places that I could not even have imagined, but you know, it ultimately, it cost my life.
Yes, every great leap into the unknown carries risk, my dear Magellan. But you, with your voyage, you changed humanity's understanding of our world. And what endures is the willingness to venture beyond what we already know.
I see, so I'm very happy to see that. The age of exploration has never truly ended.
It didn't. It simply found new oceans to cross. Thank you, Ferdinando de Magalhães, a.k.a. João Pequenau, for this introduction, which puts us in the right spirit for this session, Space, Ocean, and the Thirst for the Unknown. This is a session in 2 languages, so we're now talking English, but we're going to have a guest in French very soon. And so if you don't understand French, you're welcome to take your earphones. So, Ferdinando Magalhães, it's time to introduce our panel and call them here on stage. Will you help me?
Absolutely. I mean, that's a new exploration for me. So I see that the first one in my chart, you know, like it's Megan, Christian. Oh, I see, like, in my time, it was also the Christians that were, like, doing these exploration trips. I see, like, it's still about
they
the same.
They sponsored you, actually.
Oh, yeah. So she's as a reserve astronaut. What's an astronaut?
Somebody who navigates through space instead of through the what? Through thin air, where
what
the air is not longer there.
Are possible in the 21st
Please, Megan,
century?
welcome on stage. This is your seat. Who's next?
Next is Didia Maria Portillo Quintero. I see that she's an experimental physicist at CERN from the Atlas experiment. This I understand. Atlas. I also used charts and atlases, so you still do the same.
Well, more or less, Dilia Portillo Quintero of the Atlas experiment at the Large Hadron Collider will tell us more about it. Please take a seat. Who do we have now?
And then, well, this actually is pretty appealing for me. It's Valentina Venturi. We are doing adventures, right? Venturi. I see, very funny. So she's an engineer, formerly at CERN, and now CEO of Effetto Venturi.
She's indeed an adventurer and a sailor and an engineer. Valentina, welcome on stage. So we have another guest, but she's not exactly here with us, but we're going to talk to her anyway through that screen.
Whoa.
And I'm going to switch to French. But before that, I can tell you that this lady, she beated you by far.
She beated me?
Yes, your ship, the Victoria, without you on board, because you're dead already, was the first to complete the very first circumnavigation of our globe.
Whoa.
37 miles, nautical miles, around 60,000 kilometers. But it took her 3 years and 27 days. This lady also circumnavigated the globe, but through a shorter route. She was smarter.
She was
and more
smarter than me?
courageous. Yes, she went around
Oh.
Antarctica to circumnavigate the globe. And she did it, listen, in 76 days.
76, not months,
Not
days.
months, days.
Oh,
so
my
she
God.
beat the record for the fastest single-handed, non-stop monohull circumnavigation by a woman in the last Vendée Globe 2024. And I hope we have Justine Métraux with us soon. But before talking to her, let's see a clip
And she had a crew with her?
with her revenge. No crew.
Oh, okay.
Monohull, single-handed.
You know, I was actually...
You cannot say that word.
Well, no crew, no
screw.
screw. You said it, not me.
Yeah. Okay, let's take a look at the video of Justine's achievements before talking to her. Look at that.
Yes, I think for sure. Overall, my feeling is good. It's I think I ticked all the boxes I could have wished before to leave. But you need for sure to have the good weapons to try to be competitive. I didn't have major issues with the boat during the race as well, and for sure then it's about speed and performance to try to be the best. During the race, when we have sales issues like I had with my J0 who broke when I was in the Southern Atlantic, then we have help from North Sales as well, trying to find the best way to fix the sails and find solutions. I'm happy with my race and with the time I set, but for sure you also think there are a lot of small areas where I could have done better, so there is always room for improvement as well.
J'espère que nous avons le plaisir et l'honneur d'avoir Justine Métraux avec nous depuis Lorient, je crois. Elle est là. Merci Justine d'être avec nous. Merci beaucoup d'avoir pris le temps. Nous avons un public de Genevois comme... je peux te tutoyer, Justine. Je suis navigatrice, pas comme toi, mais j'aimerais pouvoir te tutoyer. C'est un honneur pour moi. Oui, tu nous entends?
Bonjour, oui, pas de souci.
Ah, ça coupe un petit peu. Où es-tu en ce moment, Justine?
Alors en ce moment, je suis à Chauzet. J'étais en week-end de navigation, donc la connexion n'est pas super. Mais j'ai réussi à trouver du réseau dans le seul hôtel de l'île. Donc j'espère que ça fonctionne quand même.
Pour le public qui ne le saurait pas, Justine, elle a commencé à naviguer sur le lac Léman, toute petite. Et après, dès les 16 ans, elle a pris le goût à la course au large. J'ai une question pour toi. Est-ce que c'est l'esprit de Magellan, que nous avons ici avec nous, qui t'a poussé à dépasser l'horizon du lac Léman pour arriver à circumnaviguer toute la Terre?
Oui, en tout cas, je pense que c'est une inspiration. Et en tout cas, pour moi, en tant qu'enfant, ça m'a toujours fait rêver de voir, de découvrir le parcours des grands explorateurs, d'être devant une carte et de voir tous les différents endroits du globe, les différentes mers, les différents passages. Et j'ai eu la chance aussi de naviguer dans le détroit de Magellan quand j'avais une vingtaine d'années. Donc de prendre le même passage que lui, il a utilisé pour pouvoir faire son tour du monde et pour pouvoir découvrir cette nouvelle route qui ne passait pas autour du Cap Horn. Donc oui, c'était inspirant pour moi de voir tous ces parcours.
Et aujourd'hui, est-ce que la voile, ça reste une passion ou c'est juste un métier?
Non, ça reste une passion. Je pense qu'on le voit aujourd'hui. Ce week-end-là, j'étais en croisière. Ça m'arrive pas très souvent non plus. J'essayais aussi plutôt de varier. Mais bien sûr, c'est important que ça reste une passion pour qu'il n'y ait pas de lassitude, pour qu'il y ait toujours la bonne envie aussi d'aller faire les courses et de préparer ces courses qui demandent aussi beaucoup d'énergie et beaucoup d'engagement.
Vous construisez en ce moment un nouveau bateau pour le prochain défi. On est au CERN. Est-ce que vous pensez que la technologie pour naviguer est aussi importante que pour les manips du CERN?
Oui, en tout cas, c'est une partie importante de notre sport. Vu qu'on navigue un peu comme on dit sur les Formule 1 des mers, pour nous, on essaye aussi d'avoir les bateaux les plus performants pour partir. Et après, c'est aussi lié à qu'est-ce qu'on va en faire le moment venu. Il faut aussi avoir un peu de réussite, pas avoir de gros soucis, et puis essayer de mener le bateau au mieux, d'aller le plus vite possible avec les compétences et les performances qu'il peut atteindre, et puis aussi de choisir la meilleure route possible.
Alors, dans notre panel, nous avons aussi des navigatrices, clairement pas aussi pro que toi, mais par exemple, il y a Valentina Venturi qui était la présidente du Yachting Club du CERN, qui était aussi nationale de voile en Italie et qui est ingénieure aujourd'hui. Mais peut-être, Valentina, tu veux poser une question à Justine? En anglais aussi, si tu n'es pas à l'aise en français. Il faut donner le micro. Non, non, tu fais rien.
Déjà.
Voilà.
Ouais. Oui. Bonjour Justine, c'est difficile de te voir live parce que tu es toujours autour du monde, mais j'ai eu la chance de te connaître quand tu as présenté la Volvo Ocean Race avec ta sœur. Donc je voulais juste dire congratulations pour toutes tes aventures.
Parfait. C'était pas une question, c'était des félicitations. Je ne sais pas si Megan, tu veux lui poser une question. Megan, c'est une astronaute réserviste de l'ESA. Elle a passé une sélection sur 22 000 personnes. Elle a été sélectionnée dans la réserve de l'ESA, dernière sélection. Et maintenant, elle prépare une régate avec moi. On va faire l'Arc 2026. Mais elle commence tout juste la voile. Donc, peut-être...
Bon.
Excellent.
Je fais en anglais. So, do you have some advice for somebody who is doing their first ocean crossing this year?
Yes, so my advice would be to prepare well, yes, just to try to think about everything you need on board and practice a bit with the shorter legs if you can, but also just to enjoy a lot because it's always a big adventure to have the chance to do that and to cross an ocean.
Thank you very much, Justine. Do you have a question? We have a physicist who explores dark matter with the ATLAS experiment at CERN, and she also has a question for you.
Yes, I was curious to know how was the preparation? How did you prepare, but mainly psychologically, because you are going to be alone in the ocean by yourself. How was it before going into this super long trip?
Yes. So, yes, we prepared for at least 2 years. For me, it was a bit longer than that, the preparation with all the training, shorter races, like transatlantic races, to prepare for going around the world on my own. And mentally, we can only prepare before the start. While we are racing, it's really forbidden to have conversations with a specialist of mental preparation. But before the race, for sure, I think all the skippers of the Vendée Globe, they work on their mental preparation, trying to, like, for example, be clear about what you can control or not, what your goals are, what you want to achieve, and also try to prepare a bit the ways of thoughts, like if you have different issues, the way you want to think about them and the way you want to react. Also, not only like what you're going to do, but also mentally to be able to deal with the issues that for sure you'll have at some stage. We don't know which ones, but we try also to prepare that to be better prepared before we leave.
Okay, is there a question from the audience? We can take a question. On peut prendre une question aussi en français du public, parce que Justine, elle n'est pas physiquement avec nous. Par contre, avec les autres panélistes, on aura l'opportunité d'aller au globe ensemble à la fin pour prendre des questions. Donc, s'il y a une question du public, je crois qu'il y a un micro qui tourne dans l'audience.
En fait, j'ai une question. Avant.
Ah, mais Magellan a une question.
Alors, je suis d'abord, je suis un peu fâché parce qu'elle m'a battu. Hein.
Elle t'a battu.
Mais à part ça, j'étais étonné par le design de son vaisseau. Et je vois qu'il y a une espèce de ailes qui sont là. Alors ça, dans mon temps, ça, il n'y avait pas. Donc je pense que c'est de la triche, c'est comme ça qu'elle m'a battu. Alors je veux bien savoir qu'est-ce que c'est ça.
Est-ce que c'est de la triche d'avoir des foils?
Oui, c'est vrai que c'est une partie de l'évolution de nos bateaux. Effectivement, aujourd'hui, on navigue sur des machines qui sont complètement différentes de celles de l'époque de Magellan. Et effectivement, depuis une dizaine d'années, on a ces sortes d'ailes que vous voyez sur le côté du bateau qui s'appellent des foils, qui sont des grandes pièces en carbone qui font à peu près 300 kilos chacune. Donc, c'est vraiment des grosses pièces mécaniques. Et donc, ces foils, on peut les sortir ou les mettre dans le bateau. Et l'idée, c'est que ça fonctionne un peu comme des ailes d'avion. Ça va créer de la portance, pour le coup, sur l'eau et pas sur l'air. Mais voilà, ça va permettre au bateau de décoller, d'aller de plus en plus vite parce qu'on n'aura plus le frottement avec l'eau et ça rajoute aussi de la puissance dans le bateau. Donc, cette évolution-là, elle a permis vraiment de rendre les bateaux du Vendée Globe rapides.
Très bien, ça permet de s'envoler.
Bon,
Oui.
la triche.
Vraiment, s'envoler. Voilà.
Ben, les autres bateaux les ont aussi, donc c'est pas la triche. Hein. Tout le monde les a. No question from the audience. There's a question from Valentina. Go ahead.
Justine, how long does it take to finance a project like the Van de Globe?
It really depends. For me, like it took a bit of. I tried to do the Van de Club in 2020 because it's 4 years, and for this one, I didn't manage to find the funding. So then I tried again in 2024, and then it worked. So I mean, it really depends. Sometimes you can have the opportunity quickly, and sometimes you can spend years, and without really managing to find the sponsorship. So yeah, for me, I would say it took me like 4 years to manage to find all the finance and to build the project.
Thanks.
One last question. What's your next challenge? Le prochain défi.
Yes, so next challenge, as I don't have a boat this year because we sold the old one you saw in the images to another skipper, and I'm still waiting for my new boat to finish to be built. So this year I'm trying more to sail with other teams, and I'm going to sail a bit with Boris Herrmann, who's a German skipper. And we have a crewed race going from New York to Lorient, and it starts the 1st of September. So all the summer, we're going to prepare with that and be ready for the race in September.
Thank you very much. Merci beaucoup, Justine Métro, pour avoir pris le temps d'être avec nous ce soir. La prochaine fois, on te voudrait personnellement et aussi pour t'amener visiter les sous-sols du CERN pour voir ces expériences magnifiques qu'on a sous nos pieds à 100 mètres sous terre. Merci beaucoup et bonne continuation. Magellano,
merci à vous tous.
You can go.
Bonne journée. Au revoir.
I'm going back
Back
to
to
my
your
time, inspired by the 21st century.
And who knows, maybe history of navigation will change after you. So we can continue with our next guest, who has a lot in common with Justine Métro. We already understood that from your questions, Valentina. So Valentina Venturi has a bachelor's degree in aerospace engineering, a master's degree in chemical engineering, and she spent 8 years at CERN doing research, and her PhD was in cryogenics, so again, a different form of engineering, working for the Large Hadron Collider. But after that, you went back to a different kind of adventure. You didn't continue with research. You did something that combines engineering and sailing. How is that possible?
Yeah, so thank you. It was more like a need at the beginning. It was more like an opportunity I saw. I saw something missing in the market that was a robotic buoy for regattas, because normally when you go and sail around these little courses and the wind changes, you have to wait a long time before the people organizing will move the buoy on the right side of the course compared to the wind. So I was sailing with Cassandra, my friend that is here tonight. We had the pleasure of looking at the drones while we were there waiting for the nth reset of the buoys. And we thought, this is something missing here. So as I was finishing my PhD, I started in the weekend to build something at home. And yes, at some point, I managed to make a prototype.
That's it.
That was my prototype of the buoy, together with my cryolino. I call it like
Cryolino
this.
Is an experiment, not far from this building.
Yeah, exactly.
On the CERN campus.
I was very close to here.
Yeah.
So yeah, that was job, and the other was the weekend, hobby that became now a full-time work.
And I mean, you created a startup called Effetto Venturi. Venturi is your name, but Effetto Venturi is also something technical that is very related.
I studied aerodynamics, and also like this idea of acceleration of a flow makes me think about accelerating the way you prepare a course in sailing.
Yeah.
Also, I was working in accelerators, so it was quite funny for me.
But starting a startup has the same sort of risks as sailing into the unknown, like Justine does.
You never know if there is a storm coming. Yes. So I started here with my prototypes, and then I remember as soon as I started the first products, and I had clients waiting for them, there was a shot of the production of chips, electronics, so that is very comparable to a storm. And yes,
But the end,
You
it's
can
a
see-
success,
Yeah.
success story. This is where.
Yeah, this is Marseille. This is the Olympic Games. At some point, they were looking for robotic marks because here it's forbidden to anchor. So there is a big problem now with the Posidonias being scratched by anchors all the time, especially in the south of France. Now it starts in Italy and many other places. So this is a way to avoid destroying them.
So you were the very first supplier of robotic markers for the Olympic Games
Yeah.
in Paris 2024. The sailing was happening, of course, in Marseille on the Mediterranean. And it's great. So what's next? Is the startup continuing? Are you still calling it a startup or is it a proper company?
I don't know. I still fit in some grants for startups, so I can call it startups. And yes, the idea is to build now a little boy that is almost ready for other kind of activities like research, sampling, taking of water, measuring, anything can be useful for the researchers. And without
respectful of the environment,
without destroying coral reefs and stuff like that. Yeah.
Thank you for your great testimonial, Valentina. You will be able to ask her questions after this session. We all move to the globe, and we can have a meet and greet and speak to all of the panels directly. Our next guest is another champion embodying the values of this evening. Of future explorers. Actually, you are already an explorer and also a future explorer, Megan Christian. Megan has 4 nationalities. She speaks several languages. Her career started in material science research that brought her from native Australia to Bologna with the National Research Council, then from there to Antarctica, and finally space. So was this in your plan? This is quite a special itinerary to get to space.
It was not a plan, definitely not a plan. I was one of those children that changed their minds every single day about what they wanted to do with their life. For a while, I wanted to be an actor or an architect or a marine biologist, a diplomat. But then I knew that I loved problem solving and I loved sciences. So I ended up doing a degree in engineering in industrial chemistry, so very similar to chemical engineering, actually. And then after that, I still wasn't sure exactly what I wanted to do, but I decided to stay on and do a PhD. And so I was working on nanomaterials for hydrogen storage. And you see, none of this has anything to do with space. But sometime along the way, when I was working for the National Research Council of Italy during my postdoc and subsequent research, I had this opportunity to go and spend a year in Antarctica. And that came up because I was working there in the lab, but the National Research Council has permanent observatories there. And so they send an email out to everybody and ask if you want to go and, be part of the crew. And I got this email and I thought back to when I had been 12 years old at the International Antarctic Centre in Christchurch, New Zealand, and just this fascination that I had with the place. And but then I didn't apply because I thought there's no way they would accept an application from someone like me. I was a materials scientist. They wanted somebody to do atmospheric physics and meteorology, so I just didn't think that was possible. But a year later, this came around again, and I thought, you know what? I'm just going to send them an email, see if they'll accept an application from someone like me. Turned out they did, and I found myself heading to Antarctica for what was really a life-changing experience. And it was while I was there experiencing temperatures of minus 104 degrees Celsius, 100 days of complete darkness, high altitude, working in this small international crew, that I convinced myself that I could do something in a field that wasn't my own background, and I could learn it and enjoy it. And that's what took me to then apply to become an astronaut.
Right. Before talking about the selection, which is a very interesting thing, I just wanted to underline Antarctica is really the most uninhabitable place on the planet, and conditions very close to those of space. I've been there myself, but in Concordia 2 weeks, and all in all in Antarctica 1 month. You've been there for a year.
Yes.
And the winter is crazy. It's temperatures minus 100 C.
Yeah.
And it's dark for 4 months in a row. How do you survive those conditions? Nobody can come and fetch you. Nobody can fly there during winter. So you have 4 months there in the dark with -100 outside, with a bunch of people, like a dozen people. How do you survive that?
Yeah, it's tough. So there are 3 bases in the interior part of Antarctica that are open during the winter, and this is Concordia Station. It's also called White Mars because it's the closest thing we have on Earth to what it would be like to go on a mission to Mars for a series of reasons. But the conditions are really tough, and I had to go outside and do my work every day. And there were moments of, well, I think those conditions, the isolation, the not having sunlight, they do play havoc with your sleep patterns and with your emotions. And so if you feel a little bit down, you'll really feel quite down, right? The converse is also true. And there are also moments of boredom because, you know, you have these very routine tasks that you have to do. But all it takes is just thinking about what a privilege it is to be there, taking a few moments to let your eyes adjust to the darkness and look up at the stars. And I can tell you the polar night sky is something absolutely incredible. And in fact, I would do this quite often. On a moonless day, I would look down and see my shadow in the light of the Milky Way. That's how bright the stars are there. So, I mean, yes, there were hardships, but it was absolutely inspirational.
And then it's a different sky to the one we, at least, are accustomed to. You were born in Australia.
Well,
so
I was born in the UK, but
sky.
grew up in Australia, so I was quite used to the southern sky. So, yeah.
And I understand that has inspired you to then try and go to space and take part in the selection, astronaut selection. I hear there were 20,000 candidates applying for becoming the next member of the astronaut team.
Yeah, and of course I did not expect to get through. Yeah, there were 22,500 applications from all across Europe, and eventually 17 of us were selected. But it was about an 18-month process, and they tested us on things like physics, maths, memory, hand-eye coordination, logic in the first stage. And then we went through to a psychological testing round where we did teamwork exercises and pair exercises. Then we went through a full week of medical testing. And then we had a series of interviews before the final selection was made.
17 selected out of 22,000. So first thing to do is to study hard. If kids want to become astronauts, get a PhD. That's the first thing.
So
something.
Yeah, and it doesn't have to be in the field of space. You know, I'm a material scientist. The only I did have some things to do with space, but in a very minor sort of way. And we all really come from lots of different backgrounds. So the key is to follow your passion and be doing something that you enjoy. So then if you become an astronaut, then that's kind of the cherry on top.
Yeah. So now you divide your days between your current job at the British Space Agency and training as a reserve astronaut. What's your typical week or month like?
Yeah, there's not really a typical day, to be fair, but training, because we come from different backgrounds, scientists, engineers, doctors, and pilots, we all have to learn a little bit across a lot of different areas. And so that's a number of different sciences, both. And a lot of this is in the classroom. We spend a lot of time in the classroom, but the photos are more interesting of other things that we do. So we work in the lab as well, because the aim is to go and spend time on the International Space Station or on a future space station or on the moon eventually. And when we're there, we'll be doing experiments. So we have to learn how to conduct those experiments. We also have to learn in that vein, some of my favorite classes were the medical classes. So we learnt how to draw blood because we are the guinea pigs when we're on the space station. So we have to be able to draw our own blood and analyze it. But also things like doing stitches in case something happens to a colleague. We also spend time in weightless conditions, so on parabolic flights. You saw a video of one before, but also underwater. That's the way that we train for extravehicular activities or spacewalks. We use the buoyancy of the water. We spend a lot of time in the gym. We do survival training because if we launch and have to abort the launch for some reason, we might end up somewhere far from the emergency services, and we have to be able to survive in those conditions. So it's really varied, and to be honest, it's a lot of fun.
It's a lot of work, but it's a lot of fun, obviously. So when this reserve team of astronauts is being trained, just in case an opportunity appears, you don't know when this will come up.
Yeah, so out of the 17 of us that were selected, 5 are career astronauts. So they were employed by the European Space Agency. They went straight into basic training, and they're waiting assignments for long-duration missions. One of them is on the space station now. The rest of us make up the reserve. And so we continue to build our own career outside of the European Space Agency. At the same time, we do this training, and we wait for a mission opportunity to become available. And largely, that's dependent on our country. And those of you from CERN will know very well one of my colleagues, Sławomir, who recently went to the International Space Station on a mission funded by Poland. And yeah, he was one of the first 2 from my class to fly. So Marcus from Sweden, and then Sławomir. And so those opportunities are coming up more and more. There are commercial short duration flights to the International Space Station. It's not just the traditional 6-month duration flights anymore. And it's opening access for more people. And in particular from the UK, we have an astronaut with a physical disability. And so he's working on a feasibility study to see what is required for somebody with his disability. He has a leg amputation. What's required in terms of training and in terms of equipment that he will need to take to space.
Yeah. So you are accustomed to next challenge and next challenge. Since you don't know exactly when you're going to fly, what is your next challenge in the shorter term?
Well, that is with you, Paula.
Yeah.
We're going to be on the Atlantic Rally for Cruises, crossing the Atlantic from Las Palmas to St. Lucia, departing on November the 22nd. And I'm not a sailor so by background.
Well, it's a talent.
I am now. I'm learning. It's another one of those big learning curves that I love so much. And, I'm always chasing adventure and the new challenge. So really looking forward to this one.
And we are taking science on board, like this object, the mini pigs. Can you say a few words about it while I show it?
Yeah, absolutely. So this is a really nice project, which is generally about teaching everybody to see the unknown, essentially, because this is measuring basically cosmic particles that are constantly arriving everywhere around us, but we don't think about them because we don't see them. But with this device, you can actually visualize them, and we'll be able to continue to do this as we go across the ocean, and hopefully inspire a few children to think about heading into this path in the future.
Yeah, this is exactly for school classes, and there's going to be a way to follow us while we cross the ocean, and at the same time a way to follow the cosmic ray tracks that my boat registers during the navigation. Okay, so once again, you will be able to ask questions directly to Megan and myself after this session. We go to the Globe and we can talk about this and whatever curiosity do you have. Now, before we transition to our next record-breaking guest, Delia, I would like to show you what CERN is all about, because she's one of the 15,000 scientists working at CERN in the Atlas collaboration. And it's important to let you know what we do and how we do it very quickly in a short clip before we talk to how she chases for dark matter.
This is a particle collision.
2 proton beams meeting at nearly the speed of light inside CERN's Large Hadron Collider.
To make this happen, you need a 27-kilometer accelerator ring, superconducting magnets, temperatures colder than outer space.
You need thousands of engineers, physicists, and technicians. Dozens of countries collaborating and sharing knowledge.
For that, you need decades, if not centuries, of physics research.
But most importantly, you need a facility that transcends national boundaries, where the scale of the collaboration matches the scale of its ambitions.
We keep developing new accelerators and new technologies, and along the way, many of them find applications beyond fundamental research.
Accelerators are used for cancer therapy.
Detectors for medical diagnosis.
Superconductivity could transform the landscape of energy supplies.
And a tool created to share information became the World Wide Web. When particles collide, new particles emerge.
This happens roughly 1 billion times every second at 4 points around the accelerator.
4 experiments, 4 giant detectors, all built to capture the aftermath. To cope with the huge amount of data generated by the detectors, you need a state-of-the-art computing infrastructure. You need data centers, around 170 of them, linked through the worldwide LHC computing grid.
You need more than 17,000 scientists making sense of the data.
Eventually turning these numbers into evidence, patterns, and discoveries.
We have observed a new particle consistent with a Higgs boson.
The LHC is now entering a new phase, the high luminosity LHC.
More collisions, more precise detectors, and more chances to spot rare processes or unexpected phenomena.
Opening up a new chapter in our understanding of the universe.
Voila, that was a proper introduction for you, Gilia Portillo Quintero, particle physicist at the Atlas experiment, one of the 4 that you saw, actually the largest of the 4. Your path, Gilia, starts in Colombia, then you went to Paris, then Grenoble. Finally, you landed at CERN with a Canadian institute. Same itinerary as Magellan, more or less.
Yes.
An explorer.
Yes, I see myself as an explorer. Yes, different countries, different people, culture, languages, different laboratories, ideas. So it always was living a familiar territory, a familiar shore, and not knowing what is going to be next, just starting a journey. And this is very similar to what happened in science. In science, where we have our questions, and we start the journey without knowing what is going to be the arrival, what is going to be the destination. So yes, I see myself as an explorer also. Here at CERN, we don't explore the space or maybe deep in the ocean. We explore matter itself, which is quite interesting because it's very near, but it's very difficult to see, and you need to be quite clever to study the building blocks of the universe.
Yes, maybe I'll give you.
Yes.
I'll give you that clicker.
Thank you.
So we saw in the clip that in 2012, your experiment with the CMS experiment discovered a particle that was sought after since 50 years, the Higgs boson. Was that discovery more or less like finding a new country or a new planet?
Yes, it could be like this, because when you explore, you have maps, right? So sometimes the maps have islands that you miss, guesses, lands that is not yet there. And for us, as a particle physicist, our map is this, the Standard Model. The Standard Model is this theory that explains what are the elementary particles, how these particles interact, but there was a missing piece, which is actually in the center of our map. And here you can see it is the Higgs boson, and we have not seen it before. So in the 60s, theorists predict this particle exists. It's like predicting, okay, there is an island that we have never seen, that is far away in the horizon, and for that, we need to build super awesome, powerful chips, vessels, new compasses, new technologies, in order to try to start this journey and find this faraway island. So this is what we actually do. We build, we build these awesome, huge experiments, Atlas, CMS. We build the largest, biggest, more powerful particle accelerator, the Large Hadron Collider, the one you have seen, 27 meters of circumference, accelerating protons almost at the velocity of the light, and then colliding inside these detectors. And then it requires 50 years from the theory saying there is a Higgs boson to actually discovered the Higgs boson. This is a very interesting one because this is a real event in the Atlas detector of a Higgs boson, one of the earliest one. But you don't need one. You need several and see it one after another one, so it's statistically significant. And then in 2012, we discovered this island. In the 4th of July of 2012, we see a Higgs boson. And this was super important because actually this particle gives masses to the elementary particles. So everything you see, the atoms, the molecules, this chair, me, you, us, the air, the universe, everything exists the way it exists because the particles has that right masses, which is evidence of the Higgs boson. So the Higgs boson is super important. And actually, you can see this is the equation that actually explains the interactions of the standard model. So this is like our map, our chart. And the Higgs boson is actually in half of the terms of the equation.
So, but does this map tell you everything?
So, no. Actually, this map is incomplete, which is great, actually, because it means it's an invitation. For us as an explorer to have an incomplete map is awesome. So, yes, this is a beautiful map. I think this is the most beautiful map ever made by human.
If you understand maths,
yes.
I think so.
But it's, okay, you can see a lot of Greek symbols, but it's to condensate everything that we know in the most fundamental level of nature, all the fundamental particles and how they interact in 4 terms. How beautiful is this? And actually, this was from a woman, Emmy Nether, that discovered the symmetries of nature and managed to put all these beautiful symmetries in one equation. And that is super powerful. And this map has been very successful year after year, decades. We use this map in our detectors to understand our nature in the most fundamental level. But there are still questions, which is awesome. We, for example, don't know what is the quantum description of gravity. Here we don't have a gravity explained, and that is a very important force.
We feel it.
Yes, we feel it.
Except you, maybe.
For you, it's very important, gravity. We don't have, for example, an explanation what neutrino has masses. We are now having a shower of neutrinos that comes from the sun, but we know they have masses, but this equation does not explain why. The universe is made of matter and not antimatter, and we don't know why. And, super important, we don't have a description of dark matter. And we know that it exists. So this is not a failure.
How can you know something dark that you don't see exists?
Yes.
How do you know that?
So how do we know? Because the universe tells us in so many different ways. So there are, for example, when we look in the stars, when we look at the universe, we see, for example, how galaxy rotates. And actually, galaxies are rotating a bit faster than what we expect. Or when the galaxy, maybe we don't see it, but okay, you have to believe me. When galaxy collides, there is a lot of matter that passes through without feeling anything. And the luminous matter starts to interact there. So we see from the structure of the universe, the dynamic of the galaxies, how the big things interact with each other, which is gravitational, that there is something that is missing. There is something that we cannot see, and we just know it by its gravitational interaction. So
it's by observation.
It's by observation. And everything that is that interacts gravitationally is because it has matter. And everything that has matter is because it's a particle. So there has to be a dark matter particle. But we don't have it yet, seen it, and we are looking for it.
How would you look for it?
We look for it everywhere. So we have satellites in the space looking for maybe gravitational effects, for example. We have detectors underground full of water waiting for maybe a dark matter particle that passes by and interacts with an atom. And we have LHC. And LHC is super cool because it collides protons, okay, we know that. But it collides them at super high energy, so high that it kind of recreates the early moments of the universe, the Big Bang. So everything that we know, all the matter is created in the Big Bang. So how we cannot create dark matter as it was created in the Big Bang at the LHC. So at that high energies, we hope that we can create dark matter particles. So we are looking for it with our beautiful Atlas detector, for example. Oh, okay. So yes, we look for it. And then, and it's very interesting because actually, dark matter does not interact, so we know. It's neutral, does not interact. We cannot see it. So how can we actually
just
yes.
corner it?
So the thing is that we use a very basic concept, which is the energy conservation. And in the detector, we know if there is something missing to conserve the energy, this could be related to dark matter. So if we have a lot of activities, something that is happening in one side of the detector and nothing in the other side that is balancing, something invisible, some energy that is not like making us conserve the energy, we say, okay, this is a dark matter candidate. But we need to see this so many times to really be able to say, okay, we saw dark matter.
And in the process, you develop new technologies, and you try to find new materials and things that then have some use, revolutionary even sometimes, like the World Wide Web, that revolutionized our world and came from this kind of experiments.
Yes, this is something very interesting because when you need to do these kind of journeys to the unknown, as for example, dark matter or discovering the Higgs, you need to develop a lot of technologies. One is, for example, the World Wide Web. So here in the 80s, we developed,
your community.
Before me, the World Wide Web, in order to really share this information around the world with different servers. So, it's very interesting because everything, the access you have on Instagram to your cell phone is actually because there was someone that invented the World Wide Web time ago at CERN. At CERN, there was also the capacitive screen, touch screen. Right. So in your cell phone, you can actually touch your screen because someone at CERN thought in this idea of having a touch path in order to control an accelerator. But there is also medical application, in medical imaging, in oncology for cancer treatment. So there is a lot of applications that we didn't think it was the destiny of our journey, but were some products that happened when we were trying to find these super fundamental questions. For example, when Einstein proposed the general relativity, he was not thinking on the GPS.
Absolutely not.
He was thinking, okay, general relativity, but then we use it to geolocalize things. Or when Newton thought or Maxwell in the radio and the equation of lights and electromagnetism, he was not thinking in telecommunications.
And Newton was not thinking of rockets, but
yes.
That's the laws you use to launch a rocket to space.
So we don't know what is going to be the products of this basic fundamental science, which is also super exciting.
Yes, I think these are the last words, the perfect last words for closing this panel, because it's only by getting new knowledge that you can really have a breakthrough in every sector of your life and in technology. So new technologies, especially technologies that are life-changing and that can solve global problems, can only be born by fundamental research and by new knowledge. So I would like to thank our audience for this panel. If you want to ask questions to the panelists, you can follow us in the globe right now, because here on this stage we have the next session in 15 minutes. So thanks to Dilia Portillo-Quintera, thanks Megan Christian, thanks Valentina Venturi, and thanks to Justine Metron and Magellan that opened the session.
good evening, everybody, and welcome to session 3 of the Future Explorers event with Sabrina Pasterski and Clara Nellist. I'm very excited for these two speakers. You're going to have a great time, and welcome to both of you.
Thank you.
Testing. Okay, perfect. You can all hear me. So thank you very much for the introduction. And today's session is called The Sky is Not the Limit. So I'm very excited to have Sabrina here with me. And well, first of all, thank you for traveling so far to come and see us today. You came all the way from
Perimeter Institute is in Waterloo, Ontario. So it was great. And thanks for having me. It's nice to be back seeing CERN.
Great. So we're going to start going a bit. Oh, yeah. So maybe we should introduce ourselves a little bit more first. So
Yes,
do you want
first.
me first? Okay, brilliant. So if you haven't met me before, I'm Clara. I work on the Atlas experiment here at CERN, and I work at the University of Amsterdam and NICF in the Netherlands. And yeah, my research is on top quark physics. So I study the heaviest particle that we've ever discovered here at CERN. And I also study how it interacts with the Higgs boson. And this tells us a lot about the early universe. And it also tells us possibly one way that the universe could end. So we can talk a little bit about that later as well. And then I also love to talk about science anywhere they'll let me. So I'm very happy that CERN asked me to be here.
Yeah, I'm Sabrina Pasterski, and I'm faculty at Perimeter Institute, which is kind of very, very like 10th scale size CERN just for theoretical physics in Waterloo, Ontario. My specialty is in high energy theoretical physics, so it's basically trying to extrapolate beyond what you'd be able to see at experiments from self-consistencies. And so my particular research program, I'll get into more, is like celestial holography. It's just one little niche of where we try to apply mathematics to understand like how to have quantum gravity in flat spacetimes.
Great. So we're going to go further back because, as I said, as I said, the theme of the session is the sky is not the limit, and this applies very well for you because one of the things that you are known for is for building your own aeroplane. So you built an airplane when you were 14, you started, if I remember correctly?
So it was between 12 and 14 was the building, and then the first time I flew it, though, was when I was 16. Uh-oh.
I take it. Thanks.
Clickers, yes.
Perfect.
So the right-hand one is the experimental, and then I was 9 when I was flying the Cessna on the left. Left.
And did you learn to fly the plane as you were building it, or you you built it first and then?
So basically, like in order to fly solo, say like I did my first solo in the Cessna on the left in Canada when I was 14, but I waited a bit because you have to. The airplane was based in the States. You need to be 16 to fly solo, and so you did need a sign off by a CFI who. Had experience in the aircraft, and the guy was Tron guy who used to go on Jimmy Kimmel. He dressed as Tron.
Oh wow!
With like LED lights and everything, and that's the person who was willing to sign me off to fly the experimental that I put together.
Very good. And you had to. Am I right in saying you had to take it to Canada to do that flight?
No. So this flight was in Aurora. So. But it was many years after, 2 years after finishing the build itself. So it was kind of like forever when you're a high schooler.
Excellent. And what was the motivation of wanting to learn to fly and to build your own airplane?
Yeah, so my family is just weird. The motivation was when we were like, so when I was 9 years old or so, everyone in school was reading Harry Potter. And I think I wanted a flying broomstick. And then the alternative was take flight lessons in a weird way. I really don't know how that's the natural first response of a parent trying to say, oh, you can't do that, but we can do this other thing. And so it was incredibly fortunate, but it's also this weird thing where it's like your like family basically puts everything they have into like then this vision of like what you can do to kind of try to make a name for yourself, try to get into undergrad because it's insane. And so just one story after another of trying to just be weird and different. It was roughly how that happened.
And how did your classmates react when you were talking about this?
I don't know. I think that like I remember more in high school than I remember in elementary school, but it was also like I don't know. You probably had hobbies when you were a kid. What was your favorite hobby?
So when I was in secondary school, most of my hobbies were playing football,
nice.
Which I will be watching later this evening, and being very nervous about a certain Norwegian player. And yeah, so I mostly did sports,
nice.
and because I'm I am very nerdy. I think that's not a surprise to anyone. But playing sports also then helped me to connect with the non-nerdy students in my school. And so that was also then really nice that they kind of tolerated my nerdiness, and I could tell them all the physics facts that I was learning because I was also able to play football and take part in things that some of my classmates enjoyed more than learning about physics facts.
And frankly, that's probably more important because like the kind of culture shock, I guess, is realizing how collaborative research is. And so like you're so much better off having a good solid background of knowing how to work with people and have like the teamwork of who can do what on a project, because like one person or like a small team just can't scale something. So this was very much like delaying that life lesson much later in life. And then I guess like in hindsight, there's some appreciation to like living through a story and how you can leverage that, I guess. But
yeah, but you also documented the build on YouTube.
Yeah.
Was the motivation that what was the motivation behind it? Why did you want to put it on YouTube?
So so many weird explanations for things. Like the explanation, like I never had social media growing up because like my family was weird and they were like, oh, everything you say is going to be used against you one day. Like, like they were very into that. But then what happened was that like my high school was this math and science magnet school, and the kind of cool alumni we had was one of them did some sort of Spark Notes or like Crib Notes thing, and the other one was a co-founder of YouTube. And so it was like almost like, oh, an homage to IMSA, like put stuff on YouTube. But like there's a lot of cringe, like almost like artsy, like undergrad like videos too that I would have. But basically it's just like I would definitely like have more like photos or pre-Instagram type of like documentation of said build, and then you'd go around and you'd have to network and like wait outside of like various professors in the hall to like hand a photo book of the build and a business card and be like, I want to work with you one day. I don't know what like the goal was, but it was a lot of networking as a kid. Yeah. So that's like the memories that come back strong.
Great, but then going forward a little bit, it actually helped you with your university applications,
Kinda. I mean, or at least, again, I think that there's something funny where you can imagine like, oh, being different is fun, and then there's a standard procedure, do your AP courses and do well in school, and that's how you get into undergrad. And so I had my heart set on MIT for whatever reason of like one mentor to another. That's the place you go for like tech, I guess because they didn't like Caltech, I don't know, in the States. And it's still like, maybe I didn't write it well enough in my application, or I wrote some limericks for another application, and I got waitlisted. So it's probably, I guess, a good thing. Like you shouldn't be doing crazy projects. You should just do well in school and do at clubs, and then you have a better chance of getting into Ivy Leagues.
But so if I remember correctly, then so you applied to MIT and you got waitlisted.
Yep.
And then you sent them the video of you building the
I had
plane?
these various mentors where I had been like I got a notary who was like a secretary at MIT. Peggy Yoon is amazing and nice. But like she had introduced me to other friends who could kind of petition or like say, hey, look at this kid again. But I do think that there is some part of the like, however the application teams are looking at who applies to these schools, like they want, like they don't want you trying too hard maybe or something, like they want to see that you want to keep building it. And I don't know if there was a clear vision for what would be next with that. I mean, for me there was, but it was like, you know, if you wanted to say that you wanted to go, like you're doing this because it's a thing you can do now to then work for an aerospace company, it's not clear that putting together a kit plane is really like the first step to that. There's like some more of an engineering focused trade. So there was an arc in my mind and my family's mind that just didn't line up with actually like the career trajectory of an engineer. And so like when things don't work, you learn from it.
Yeah, but I was really impressed by that because I'm naturally the kind of person that if somebody tells me no, I go, okay.
Yeah.
And so when I applied to university, I applied in the UK. When I applied, you applied to like 6 schools.
Fun.
And then you go and interview at them, and then they decide based on your grades and your interview whether or not to let you in. Yes. And I really wanted to go to the University of Manchester, and I had quite a terrible interview because it was quite a theoretical interview, and they asked me questions of stuff we hadn't covered in my lessons yet. And so I told the interviewer, I know we are going to learn that, but I can't tell you the answer right now.
And hopefully that was the right answer, because you at least know the limits of your knowledge, or they didn't?
No, he was just disappointed and just said to me, oh, well, most students have already done this by now. Okay. And so for me, then I left that interview going, oh, well, I'm not getting into that university. But fortunately, my grades then compensated.
Okay.
So I got the
Yeah.
grades that I needed, and they didn't have to look at the interview, and then it was all fine once I actually got to the university. But I'm naturally more of a person that if somebody tells me no, I go, okay, I guess those are the rules. And so I'm very impressed that then, you know, not necessarily just taking the first answer and still being really ambitious and wanting to go there, and that then comes through at the university.
I mean, yeah, I think there's value to both, both of it. Like, because you'll learn one way or the other which is good or not. I mean, maybe there is something nice about being less aware of the boundary conditions, because then you're exploring a phase space where maybe it could work out, but when it doesn't, you'll learn it too. So I guess like, but at the same time, in the academic system that you would come from, like everything just ties to like one grade at the end of the year. And that can be so stressful. I imagine some students just don't perform as well when it's like a single test at the end. And so it's a nightmare to try to navigate.
Yeah, it's very scary when you have one or two exams that define everything. But yeah, so then you went to MIT, and you originally started studying aerospace engineering, and so then you moved to theoretical physics. So what was the motivation then to go from aerospace engineering to theoretical physics?
Another bad reason. So basically, when I was little, again, like this kind of goalpost was always moving. So it's like, I wanted this flying broomstick, got an airplane instead, flying that. You meet various people at air shows because like a 12-year-old walking around is like a cute little kid or something, and then people are building kit planes and they suggest that, and it's like you're basically doing a guided random walk of like whatever a mentor suggested that then you're latching onto as the next thing you could try to do, yada yada. And so maybe by accident or not, like at the time, the big thing that was happening in aerospace were these private aerospace companies that were launching suborbital. And so the leader at the time would have been like Burt Rutan's company being bought out by Virgin Galactic and Richard Branson, and then SpaceX and Blue Origin as these kind of other like maybe more like better funded aerospace companies that were also going to be in that suborbital space. And so my goal at the time as a kid was like do whatever you can to like get into the university to then work for these guys, because it was this like the coolest thing that they were doing, like stuff that might not necessarily be like profitable now, but had this like bigger vision. And I loved that kind of long-term vision. Like I guess is a thing that I kind of latched onto. And so unfortunately or not, some of those folks liked physics or said they did at some point, and I completely like misinterpreted maybe why. Like, so there's maybe two reasons why these like aerospace folks like physics. One of them is this like same thing like tech people love quantum because they think that's where the new technology is. Like Feynman tells them, or all these other folks, like you're gonna like have a breakthrough when you can build these things. And so they see it as an engineering thing where if they pour money into a thing, they'll then have this new technology and it'll work out. Same thing, I guess, with fusion, but I guess for some reason quantum was a closer one. And then the other side of it is more of like physics is not like theoretical physics or physics like you or I know it. It's like physical world, and so it's more like fluid mechanics or things like that. That's what they have meant, and I didn't understand that. So I'm like, okay, physics. Well, what's in physics? If I want to get out of this like kind of childhood story and pivot and lean into the fact that I did well in school, like the next best option that was kind of on the approved list was going into physics. And so, yeah. And then, and within physics, it was like, oh, the string theorists like are on TV more.
Yeah, there were a lot of
So there's a lot of bad reasons, like just completely just bad reason after another to go between career paths. So.
But it's still quite early to decide.
Yeah.
Everything. I mean, what's interesting is in the UK, we pick our major right away.
That's good though, right? Because then you actually know the topic by the time you go to grad school.
Yeah. So all of my lessons were on physics, except for I did one on forensic science, which was just for fun. But it means that you don't have that period of time where you get to choose extra subjects and shop around and see what you really like to do. I mean, I'm very happy. I picked physics and I love it, and it's clearly working out well. But I think having to decide at 18 is also still very, very early.
Sure, but at the same time, like I think that like there's a certain thing where it's clear, like when you have this like portfolio going in, that's the thing you're selling yourself as, and you're kind of all like latched into that, or some other backup option. So it's kind of still very myopic about what the vision of the future would be, which is not the right approach, I'd say.
Yeah, but I think even physics is a very broad subject, and there's so many different things that we can study and learn about. And so in your undergraduate, you worked on CMS, right?
So I was actually at CERN, and this was also another accident. So basically I had an advisor from undergrad who was at CERN. Marcus Clute. I don't know if you know him or if he moved around, but he was at CMS. He was at MIT at the time, and he happened to be my assigned undergrad advisor. And so when it came to thinking of summer internships, I asked him, and I ended up here for 2 summers. And it was like, I think the first summer I was here was the year of the Higgs discovery. So I was like, oh, that's easy. You know, like, I mean, you don't appreciate all of the work that goes into this thing when the first time you're there is like the biggest, awesomest thing happening for a while. And it's like, and so it was fun to see that. Or I wasn't actually there for the announcement, but I was there that summer. And like, let's please turn it on to you though about this type of things, because it must be so fun, or it's like a different kind of timeline when you're kind of like this whole procedure of like deciding what CERN's going to do next, or even like starting to build an experimental collaboration. How did you feel like when you were entering grad school? Like at what point did you realize like how the mechanics of like how a collaboration works like actually is? Because like as an intern, for example, in the summer, I'm just like told to do look at someone's service work for some like silicon like avalanche diode thing, but I'm not really like seeing the whole picture.
Yeah, for me it was a little bit different, because when I started my PhD, I worked on the hardware. So I was working on the upgrade of the Atlas experiment. Yeah. And so I had a lot of collaborators working on test beams. We do test beams here at CERN, where we take a prototype of the device and we put it in the same conditions that it's going to have over 10 years, for example, in the Atlas experiment. And then specifically, I was testing the radiation resistance of these detectors and making sure that they were going to last the full lifetime of the detector. And so when I started, I mainly focused on that collaboration. So it was still a collaboration, but it was a smaller group of people. I would be spending many, many nights in the control room with them. And so I was learning about how Atlas worked from those colleagues. And I had a different experience from my analysis colleagues who launched straight into the full collaboration, I would say. It's different now. Now we have much more integration. But when I started, I was focusing just on the upgrade.
And was that something that you felt like you chose, or that your department that you went to for like grad school, maybe like that choice was made for you in some sense? Like what made you drawn to hardware, for example?
So some of it was made for me, but I'm very much, I like being around people. And so I like to work in groups. I like to talk to people about things. I'm very happy in a control room. Yeah. I like to have a job. So for example, when we're in the control room, we're in charge of the Atlas experiment for 8 hours, and we have to make sure that it's safe, as in that the voltage doesn't get too high or anything like that. Yeah. And that it's, that we collect data and do our job efficiently.
Yeah, maybe I could try to unpack, because I think we both will have different perspectives on this, exactly kind of at what point, or what's like the formative memory of where like your vision of physics going into it, and maybe even staying like that in an undergrad, changes to like the mechanics of doing the job. Like, how was that for you?
I think for me, the moment where that happened was when I was in my master's program, and I was doing research at Fermilab on the top quark, and they sent me over to Fermilab to work there with all these international people who were doing physics as their job. Yeah. And that's for me when it switched from something I was learning about in lectures to something I got to participate in. And the measurement we were doing, it was the first time anyone had ever done this measurement. Yeah. And so that was really exciting, because I got to measure something and tell other people what the result was. And then I applied for a PhD to work here at CERN, and I was just so excited to get to continue doing that. But I didn't know I would get to do it, to continue to do it. Okay. And I was still trying to figure out what I wanted to do with my career. But the more time I spent here, for me, I was like, I just don't want to leave. Please, awesome. Can I keep working on this for as long as possible?
That's amazing.
Yeah. And for you, so then, because you were working on CMS.
Yes.
But that was still quite experimental work, right?
Yes. And to be fair, like I think it was more like if you want to go into like theoretical physics, it's very hard to have that mathematical background ready to be doing that type of research if there isn't even our opportunities in undergrad, for example. So it kind of pushes things later. And then in the States, you don't really have to apply for a master's, so you can get into your grad program based on your CERN experience or anything else and pivot there, which I guess is good if you want to change your mind, but also a little bit, again, haphazard in the sense of like you don't know who you're going to go work for as advisor, and in hindsight, it's like your advisor is everything to your future. You should be thinking about that more than the university, for sure. So for me, I think the funny thing was like I came from a background with a bunch of aerospace folks, and like aerospace engineers are fun. Like I mean, like first of all, like the view of an engineer towards something theoretical, like they didn't necessarily understand the value of like say doing theoretical physics, but at the same time also this vision of like what was possible or not, somehow like very like crazy sci-fi things were seen as like the future when like that's like physically not possible, right? So there was this kind of jading of like, oh, like we can do anything, and then very much like no, and then also like maybe a vision of like when you think of theoretical physicists, you think of them maybe like debating quantum mechanics or whatnot, and like you rarely like spend your time really thinking of the foundations of your field. You're really in the grid of like a computation, and then kind of trying to appreciate both like the sociology and also where the little thing that you're contributing to fits into that bigger picture, because it's not as top down in the sense of like people are assigned to do things except for literally by your advisor. And so it's hard to kind of paint that mental map of like what's actually possible now, what people are doing.
Yeah, but you did then move into the
like more and more theory,
more and more in the direction of quantum physics and
or I'd say that it's quantum field theory and like high energy theory isn't. Like it's quantum only in the effect of like that you have loop computations, right? It's not exactly like quantum physics that like a pop sci person might think of, but more fundamental, I guess. Yeah.
Yeah, and so the next slide we have is what I want to lead into then your current research, because this is very familiar to particle physicists. This is the standard model of particle physics, and we have the fermions, which are the matter particles, and we have the bosons, which are the ones related to the force, and we have the Higgs discovery, which was an incredibly special event. You were mentioning that you were here that summer. It was just a huge achievement here at CERN. But when we talk about the fact that the bosons are related to the forces, there's one missing in that model, which is gravity. And we don't have a quantized particle for gravity currently in the standard model.
And you see, and this is the funny thing about like theoretical work and sometimes where you can miss like what the experimental side of it is. I think that there's a funny sense in which like we all believe there's a graviton. Mm-hmm. We don't think we're necessarily going to see it in our lifetime, but like we just completely are like, oh, we know it's there. Like we know how to treat it like a low energy effective field theory and things like this. Mm-hmm. So it's so there's this. It's also weird to know. But at the same time, what that comes with is like the types of things that you want to think of as physics. Is it really new physics? And I think we're bad at like seeing that like things where you generalize and find an experimental like check, like that is, in some could argue, just as new physics as like a new field or something like this. So we have sometimes, or at least I've found personally, maybe like me and my colleagues can not always appreciate like how to see something as new when you're always just like building off of these kind of key ingredients of like symmetry, gauge invariance, and all this stuff as like your toolkit, and you just keep throwing that at the wall.
Yeah, and so for you then, for every day, these are things that you've accepted.
Oh, I do accept, and then you have to reflect, and then you hope you change your mind because that's the cool stuff. But yeah.
Yeah, and I mean, whenever you talk to a physicist, we all have our different favorite theories and what we're working on. I'm as an experimentalist, I have a different experience because most of the time we're measuring what the detectors give us. And so I'm looking at lots of different theories at once and seeing how they fit in with our data.
And so would you say that your favorite thing is like a regime of physics or like a particle that you're interested in or like Higgs prediction?
Personally, for me, I do my precision measurements with the top quark and the Higgs. So these are ones we've already discovered and can test the limits of whether or not they fit with the standard model or whether they tell us something different, which would be super exciting. And then so we had the documentary earlier, the Anomaly Detection documentary, and so part of my research is also working on anomaly detection. And then this is quite theory agnostic. We don't have a specific theory that we're looking for in anomaly detection. We're looking for anything where the data looks different than the standard model that we already have. So that's usually my day-to-day work, and then I love talking to theorists and then hearing about when you really zoom in and then focus on one particular area and then look at the limits and how you can stretch that beyond boundaries. I mean, the theme of the session is really like how we can go beyond with physics. And so I'd love to talk more about the celestial holography that you work on.
Yeah.
And how does that go from then from quantum gravity to celestial holography? What are you looking for? What are your motivations in this research?
Fair. So like this kind of standard motivation that like almost like most like high energy theorists give is, oh, we want to have a theory of quantum gravity. And the justification for that is that, you know, very short distance physics is governed by the quantum. Very long distance physics, we see Einstein's corrections to Newtonian gravity. And then we're also like very adamant that any framework has to include like all physics. So like there's some underlying framework where I can describe both of those things. And so to the extent that we think that there could be a more like reductionist, more fundamental theory, then you need to have a theory that can handle both. When you just like treat, like there's an action principle for Einstein gravity and you try to treat it like a quantum field theory, you can actually do a lot, and a lot of my research can be treated just that way. But then what happens is like you run into issues of like, okay, there are an infinite number of counterterms, what's really happening in the UV? And then folks will go all the way to wanting to have like 10 dimensions and the stringy spectrum where you have the graviton, you have gauge fields, but then you don't know how to realize it. It's a self-consistence theory, but you don't know how to realize the real world in it. And so you're in this kind of really beautiful, like the thing that I love about theoretical physics is the extent to which we're basically saying that like the observations that we have plus some extra like mathematical assumptions, like the math can take us beyond like into the future of experiment. And that's the goal. And it's based on that assumption of this kind of, there is a unified theory. And then you also have these like shoulders of giants that you're building off of when you're like a grad student entering it, because a lot of people think they have that answer for what the UV physics is like. And just like string theory has so many even different like equivalent descriptions of it that there's a lot to learn. So I was fortunate that I get to spend my research on something slightly more terrestrial, which is this notion that, okay, we have quantum field theory, we have gravity, we're going to be able to probably treat it like a quantum field theory in this IR limit. If I assume certain structures of my space-time, can I kind of pretend that I can just import some universal principles that appear in other instances? So for example, like basically our goal is to build like mathematical frameworks, play with as much as we can compute in that case, and then try to fold it back and apply those to more physical settings. So in this kind of history of trying to understand quantum gravity, one of these answers is, you say, string theory. And then another kind of thing you can do is just try to do more of like a Hawking kind of thought experiment of let me put my quantum fields in a curved background, and then you run into also these kind of funny things. It looks like a thermal system. My black hole has an entropy. And so from this very, I'm going to go to 10D UV completion idea, or from this more mundane, let me just tie together the things that I think I know, you both seem to see that like gravity almost looks like this lower dimensional theory. And so what physicists like to do is we say, oh, look, there's concrete instances where we know this thing has it. Let's pretend that's always the case. We're going to make that our starting assumption. And we're going to try to see how can we build a holographic description, this lower dimensional description where gravity is like a quantum field theory, for my space-time. And so that's like that we're just going to declare we're going to do it, and you start doing it, and then everyone in your field's like, oh, it's just kinematics, and then you hope that you can find actually a string example, but then it's just self-dual, and you're always basically just trying to justify why your mathematical approximation is okay or why it's useful. But at the same time, we're all just wrestling with the fact that, you know, it's one thing to have an underlying framework, and then to understand really how you're realizing the stuff that we see from it is another layer. So
yeah, so you're converting those mathematics to 2 dimensions, you said, and is that the boundary of the universe?
Yeah, so there's something kind of fun to think about, like what does it mean to go to infinity? I think we think of maybe like I'm like swimming out of shore and I can't see the shore anymore, like some notion of like space-like infinity. But you can also ask what would happen if I like turn on a laser pointer and shoot it out and there was no ceiling here. Where will that go? And in some sense, the fact that like, say I'm moving and I'm a massive guy, I'm never going to catch up with the speed of light from relativity. There really are like different directions in which you go when you're going in a time-like direction, in a space-like direction, and in a light-like direction. And so what it turns out is that there is a manifold that you can kind of attach to infinity. And when you do that in ADS spacetimes, which is like the wrong sign cosmological constant compared to the ones that we actually observe, there is this box. You basically have gravity in a box. And what you're trying to do when you're doing holography is saying, okay, there's this theory in the bulk, which is the kind of regulated and not quite the right sign gravitational theory that is equivalent to something on the boundary, and I don't have gravity, so I get to get quantum gravity for free by cheating. And then I also have the time evolutions be the same, so I understand everything. But now in the flat space case, that structure has changed, and then all hell breaks loose because you don't know what approximations you're making, and then you're like, until you're not scared.
And so what do you love about this research? What motivates you to because it's very mathematical, you're working through, you're making these assumptions, as you said, you're applying them then to what we already see in the universe, and then mapping them out in this 2D space. And what motivates you to do this every single day?
Yes. So I think that there are two facets that, like, at least, I mean, maybe as a theorist, if I would tell a new kid coming in, like, what they should try to find about what they like, what they do. One is kind of this, like, bigger picture motivation, and this is like quantum gravity or like fundamental laws of nature, this notion of reductionism and trying to understand that structure. And then the second is, like, do you like the mechanics of your job? So for you, it might be like whether you're building a detector or something with like the data processing that you actually like are just zoned in when you're doing it. And often when you're computing something, it kind of just feels off and wrong if it's not correct, and you've been doing some computations and you can see something's not working here, and so you're compelled to finish that. And for me, I definitely, like, once I'm in the computation, I'm just happy. It's like a little pacifier. And then the only parts where you get scared is when you like hear like string theory isn't cool anymore. What? Like, I thought it was cool when I entered grad school, and I think I was just like zoned in, and now suddenly like various cooler folks on YouTube don't like string theory no more. But we're still cool. We still think we're cool. We'll die on that sword, and that's not good. But in hindsight, I think like wrestling with the fact that there is this kind of big disconnect between like studying this like mathematicalization of physics and like the actual real world. I'm fortunate there are some things that are like related to displacements of detectors, so you actually do have a prediction, yes.
Mm-hmm.
Even though you're using Einstein's theory, you're just like making a prediction about boundary conditions. So I have something that could be observed.
Mm-hmm.
Just saying. But like few and far between, and it was early grad school. So they probably changed me since. But the thing that I think I really do love about physics, and this is something where I'll try to co-opt this and talk it to more of like a CERN situation, is that I think that the pursuit of like the set of fundamental laws of nature and understanding that mathematical structure is super important, because somehow physics is the fact that like there's some simple mathematics that can predict things. And so to whatever extent the laws of nature like they say that there's some highly compressed form of the way the world works, the fact that like Hep theorists somehow are part of that venture, and if anything are more reductionist, so they're really pushing for it, that's the thing to die on the hill on, not string theory in particular as the best model we have that includes both things.
So that's what drives you every day.
Yes.
And what are the challenges then of your day-to-day job? Are there days where you get frustrated with what you're doing, and how do you get through that?
Sure. So maybe the old me or whatever, just celestial world, you get frustrated whenever you like want to try to find a question that is doable and interesting, because oftentimes like the aha moments are once you've done some computation, so you want that computation to be correlated enough with something where you can then have a fun interpretation of it and then present it in a way where people find it convincing, and then sociology of how do you present it, or like, so those things can be frustrating or not. But I think the thing that I feel more passionate about now, and where like I try to bring the airplane stuff back into it, is like, you know, if I look back at the results where I probably got a faculty job off of it, what actually happened was like, basically, Sasha's also a faculty here. There's like the same mathematical equation appears in some gravitational wave paper from the 60s, appears in Weinberg computing some soft limits, also in the 60s. And just finding that those two equations are the same lets you kind of explore the mathematics around it. So Andy and his other grad students had this understanding of like word identities and soft theorems. Then you're tying that to asymptotic symmetries, and then like I was part of like understanding that was more universal. And so you're really just almost like you have a tapestry of all this equivalent mathematical results. You're folding it over and tracing it out because you know now like part of it is the same here, and you learn new things with something that's super systematic. And so to whatever extent like I could bet a career or not on hoping that I pick the right branch of a thing to then learn and have the right background material and ask the right question to dive in and have a breakthrough, like that's low odds. But there are so many systematic things you can do that do end up leading to these things, where you can try to ask, what is a breakthrough? How much of it is like compressing a knowledge canon versus opening up more things you can compute? And I'm really fascinated with these questions. And the thing that I guess I'm like trying to like like debate or think about is like maybe we as theorists need a CERN. You know, like, I mean, to the extent that you have in your library, you have a, like, InspireHep is amazing. It has, like, all of our data. That's the best, like corpus to do thing. But we don't really think of, like, an effort to try to build that infrastructure to really not just do the problems, but do that, like, that kind of meta version of the problem of, like, what is, like, the knowledge graph of our field? How do you actively try to compress it? And, like, what's the simplest, like, theory that describes these things? So I'd love to, like, pick your brain on exactly, like, maybe how, like how does one actually make different people come together and like value like building towards the thing where you're really assigning different parts? Because like hep theory right now is all like you're just one person doing this thing, and it's an accident of that's the way it should be done if you have 2,000 people. But times are changing, and there's a lot more technology to do kind of this knowledge infra. So yeah.
Yeah, but before we go on to that, I want to touch. But I want to touch on something else you said, because I think it's really important for early career folks who are listening that you cannot always map out exactly what you're going to work on and where that's going to go. And we don't have the luxury of necessarily knowing what nature, the true reality of nature is. But working on problems that we find really fascinating, that we can really get your teeth into, and having that curiosity and making the connections between different fields is such an important skill for a physicist.
Yeah.
And also, one of the things I love, and it happened the other day again, is that when I spend time with physicists, you start to see the connections between the research that we do and things that happen in the real world. So we were on a boat, and there were some waves in the water between two boats, and one of the physicists on the boat was like, oh, hey, do you want to hear a cool fact about the fact that when you have two plates and the quantum interference between those two plates and the waves that you can have there is exactly the same phenomena that you're seeing then in the wave pattern between the two boats, and it also then has an effect that the boats can pull together.
Fun.
And I just love, there's also, Brownian motion that you can calculate how molecules move in a liquid, and then you can also use that to predict whether or not you're going to get stuck in a traffic jam. And there are so many of these connections, and you were saying with the things where you were doing some calculations, and then you found that it was also the same mathematics that was in the gravitational waves, and making those connections and seeing where things go together. I think that's something that is a really good skill in physics, and it shows us just how much things are connected.
Yeah, and I think like one of your colleagues, like Sebastian Daharo, like, I mean, I don't know how much you overlap or see him because he's like philosophy of science, but like the perspective that I'm trying to like learn more of metaphysics, because it's related to this infrastructure type of question of like whether you like some dualities are such that you are literally applying them to different physical systems, which is like this kind of situation versus like, and so some, for example, when people use ADS-CFT, it's not always as this kind of wonky like gravity theory with a funny background. It's also as like the gauge theory and the boundary as some approximation that's like super symmetric of like the gauge theories you'd study at CERN. So I think that like one question can be is it that we have such limited mathematics that we see like we can only apply certain things, or is there really some universality of like these emergent phenomena kind of being something you can categorize, and that's why so many different things can be modeled, or they're like low latent space things are modeled the same way. And so what I think is super fun is like really trying to understand what a hep theorist does makes you confront the question of like what is solving physics, or what is hep theory actually going to give you? Is it possible from that fundamental description to even describe some of these emergent things? Probably not, or like at least maybe complexity is the thing getting in the way, and not so much like in principle if you have something regulating it. And so that's interesting because it also like it makes you think about what is fundamental, and yet at the same time I like the fundamental theory. Kind of like I think there's a lot of fun questions that actually we can do something with now that would have been in philosophy or foundations and stuff, and foundations of math, that suddenly becomes super relevant when you can automate away a little bit of the work that I would normally do now. And then how does it all fit together? Because I think what I'm doing doesn't make sense if you're not fitting it together.
Yeah, and then that links back to the question that you asked earlier, is how you can, I think you were saying, link the theoretical community better, or
no, I think what I'm saying is that like there's a sense in which like, I guess, like I really love my job, not because of the thing that I do, but because it's part of this legacy, and like, what's the thing that I could do now to contribute the best I can to this legacy? I think that we're at a stage where suddenly you're maybe in a couple of years, you're able to formalize mathematics more automatedly, so it'll be like a more efficient thing. And so then there's this question of, okay, theoretical physics is roughly like math applied to modeling the universe. but we often are not stating all of the extra assumptions. And so like, there's a kind of fun version of just trying to map out paradoxes as like incompatibilities between the extra assumptions you needed to do your derivation versus the thing. And so this formalization tool like would help you with that. But at the same time, like I think that the corpus is the thing that I'm studying. So there's a sense in which you're studying like the actual realization of this universe. You want to make a measurement, and you're using like physics to guide then your experiment to do that. And my experiment is instead this corpus and trying to see like what other presentations of it that are true or something like that. Infrastructure, I think, is somehow the thing that I am passionate about thinking I'm studying.
Yeah. So before, because we nearly have to wrap up, so now I want to think more about the future. So here at CERN, we've just turned the Large Hadron Collider off. We are going to be upgrading the Large Hadron Collider and our experiments over the next 4 years. And then we're going to move to the high luminosity LHC. So this is going to make the accelerator even more efficient at colliding protons together. And this will give us more data. So we're going to have about 10 times more data to collect over the lifetime, which then allows us to study really rare events and potentially look for hints of dark matter, for example. And I want to look at how the Higgs boson interacts with itself is one of the research topics that we're doing in Amsterdam and many other groups as well. And so I'm really excited about having this bigger data set that we're going to have to be able to look for really rare things. And then we're even further in the future starting to plan the next accelerator. So we had this big European strategy where we talked about what the future of accelerator physics and particle physics will look like up until sort of 2070 and beyond, which is really exciting to think that far ahead. And so in your field, what excites you about the future of what you're doing, and what are you wanting to, you mentioned about
I'm excited for, the first reason why I'm excited for AI, I mean, there's also reasons to be very scared, especially the way the big tech companies are interacting with it. So I'm not saying that it's all like rosy, but the cool thing about CERN, I mean, and Perimeter is a smaller version of it, but we have, like an events team, and we have advancement, and we have outreach, which is cool because it's not just a department, but it's just for theoretical physics and it's small. You guys have so much like compute infrastructure. You have your CERN library hosts InspireHub. You have a lot of infrastructure for the mission because you need it because you have you need to deal with the data of CERN, right? I think that there's something super cool to think about so your goal for the experiment, you have a very particular measurement. If our goal is to do to understand the fundamental laws of nature and equivalent representations of that, that is a venture that somehow needs more organization than just individual researchers. And there's a time now where that makes more sense because what you have is you just have all of these big labs roughly saying, science is the branding that's positive as opposed to we're going to take your jobs. And at the same time, the fact that suddenly I can use Claude Code for $200 a month, I can do something that I would have a really hard time hiring an intern to code for me because I'm a Hep theorist. No one needs to code in Hep theory, you use Mathematica. So you don't really have that ability to scale your research. And it's not clear that you needed to do it in the past, but once you're faced with this question of oh, we're GPT-8 is going to solve physics. First of all, what does that mean? What do you mean by that? Do you mean some other resolution of information paradox, or do you mean you've identified some string vacuum? What does it mean to you? We should be defining it. But even if you did answer one question, that's not physics. So what does it mean? Do you want an oracle? You want to understand that knowledge graph. You want to understand how concepts are supposed to be either formalized or extracted from data so it's interpretable. I think there's some really cool things where it's you have these tools that at the same time are threatening your job, but then making it so that you can scale your job. And how do physicists become involved in that part and not just be a couple of us working for the big labs and then oh, they wrote a cool paper that solved a long-standing problem. Look at us, give us more money to automate your job. I don't know. So
yeah, I mean, it's a big discussion topic right now. And in experimental physics, we've been using machine learning and AI for 30 years.
Exactly.
And
where's
now,
your cut of it? Where's the World Wide Web funding CERN as opposed?
Right, yeah.
And
now we're seeing this even greater acceleration of the use of it, and it's a really interesting question of where that's going to go in the future of physics. And I'm looking at the time, and so mentioning questions, I want to say, well, thank you so much for talking with me and for being here and having this fascinating discussion. And if anybody has any questions, we're going to move from this stage to the globe after here, and so we'll be available there to answer any questions that you have about topics that we've talked about or anything about experimental physics or theoretical physics that you want to ask. And then we also have coming up another session So the next session on this stage is going to be a cosmic adventure. So that starts at 8:30, and we invite you to also join that session as well. So any closing words in the last 30 seconds that you want to, it's a big ask.
I guess it would be like, I'd love advice on how you start like a large-scale international collaboration from zilch.
Well, you're in the right place for that. So we can definitely talk more about it. So thank you so much for joining me, and thanks for joining as well.
Good evening, everyone. Bonsoir, tout le monde. Welcome to this final session of our Future Explorer event here in the main auditorium of Science Gateway, a cosmic adventure exploring our planet and beyond. Une aventure cosmique, explorer notre planète et au-delà. This is a bilingual session. Some of the interventions will be in French, so if you don't understand French, you're welcome to help yourself with the translation headphones at the entrance of the auditorium. C'est une session bilingue, donc si vous ne comprenez pas l'anglais, il y aura une intervention en français, les autres, c'est tous en anglais. Allez chercher les casques pour la traduction simultanée. So with our exceptional guests tonight, we will explore the deep connections between a mountain hut, the International Space Station, the moon, the Earth's atmosphere, and the search for life beyond our planet. So without further ado, I would like to welcome on this stage our panel for the last session of the festival. Let's start with Jasper Kirkby, CERN scientist, spokesperson currently of the Cloud experiment, an experiment that he built, conceived, and is running still. Please have a seat here near me. Next is Emeline Bolmont, du Centre de la vie dans l'univers de l'Université de Genève, astrophysicienne. Elle est la présidente du centre. Welcome on stage. And Elisa Laudi, engineer, CERN AMS experiment previously, currently ALICE experiment at the Large Hadron Collider. Later on, we will connect to Houston. Yes, the Houston, we have a problem. We won't have a problem to connect with them, I hope. And we will talk to two astronauts, Roberto Vittori and Luca Parmitano of the European Space Agency. But we will see that later. Let's start with Jasper. So Jasper, you're a particle physicist. You're at home at CERN since a long time. You come from the UK. You were starting your career at Stanford Linear Accelerator long ago, and then you joined CERN in 1984. So what was physics like when you started studying physics, even before SLAC? What did you study? Were there particles in accelerators?
Actually, I started when I was 6 years old. That's when I started physics. My brother built a crystal radio set, and I proceeded to listen to Manchester broadcasts from 10 kilometers away, and I was absolutely fascinated. And shortly afterwards, he left, went to McGill University in Canada, and left me all his chemistry box. And I had enough chemicals to do very...
So you were 6-year-old, you said?
I was 8 at that stage.
Okay.
And I proceeded to do fantastic experiments that my parents had no idea I was doing down in the cellar, and that hooked me on science. So that was where I started.
So we see here a picture of cosmic rays, cosmic radiation. That's the origin of particle physics, right? What are cosmic rays? We are talking a lot about cosmic rays tonight, but just to start with, give us the tool to understand.
What they are particles, subatomic particles traveling through space near the speed of light. They're mainly protons. They're produced by exploding stars, by supernovae, and they're accelerated in the shock wave. When you see a photo from Hubble or whatever of a supernova, you're aware of this sort of envelope, the limit that the supernova has gone. That's a shock wave of the debris from the star, and that's actually the region where the cosmic rays are accelerated. There's a mechanism called the Fermi mechanism, and that accelerates them up to very high energies, even higher energies than we can make at CERN.
So we can say that Cosmos is a free of charge accelerator, just sending us particles all the time.
It's a free accelerator, but the intensity is very low.
That's why we need instruments like the Large Hadron Collider to make precision studies. And
cosmic rays is where particle physics started, but eventually after the Second World War, it shifted to accelerators. So starting in Berkeley, high-energy accelerators started shortly afterwards, CERN started, and really it's been dominated by accelerator science.
And cosmic rays were discovered in 1911, I think, by an adventurous physicist, Victor Hess.
Yes.
And it was an adventure all the way, because before him, there was this Italian scientist, Pacini, there was this radiation that physicists didn't understand what it was, and they thought it came from the Earth. So he took a ship, a military ship in Italy, and he sent down to the bottom of the sea a Geiger counter, I think it was, to measure how this radiation actually, if it came from the Earth, it should increase, but it decreased. And so this gave Victor Hess the idea, let's go to as high as we can as possible.
The story actually started a few years earlier than that with the discovery by Becquerel and the Curies of radioactivity. And essentially at the same time, Thomson in the UK discovered the electron. So it was then realized that the atoms had something smaller and they were made of charged particles. And right at that time, almost within a year of that, C.T.R. Wilson and German scientists found that gold leaf electroscopes, which were very precise instruments that measured charge, they stored a charge between, and the two leaves spread apart, those two leaves would go slowly back together. So they realized that there was some penetrating radiation that was ionizing the air, that was creating weak ionization. And then there was 10 years, and you've just described part of it, of intense scientific exploration and debate, and it was acrimonious at stages about whether
there were fights, right?
Whether
between
it came
physicists.
from the ground or whether it came from space. And there were many ingenious experiments. You've described some of them. There was also an experiment by Wilson himself. He took an electroscope into a train tunnel in Peebles in Scotland.
Oh my gosh.
And he did it at night because he didn't want to meet a train in the middle of the tunnel.
Obviously.
And he found actually that there was almost no difference.
Between outside and inside.
He said that looks like evidence that the shielding should have stopped those cosmic rays if it was coming from outer space. But we didn't know about radon at that stage, so he was fooled by
and then Victor Hess had the last word.
Victor Hess picked up on a very smart idea of a friar called Wolf, who took an electrometer to the top of the Eiffel Tower. The Eiffel Tower is about 15 years old at that stage. And he found that the radiation didn't decrease as much as they expected if it was coming from the ground.
Right.
But it wasn't good enough. Hess
It was not high enough.
It wasn't high enough. Hess took his balloon up at 1,500 meters. The cosmic rays, the intensity of ionization started going up, and finally at 5,300 meters. And I remember that height because it's the height of Everest Base Camp, actually, but he did it from Germany, his flight. Then it was 3 or 4 times higher than it was at the ground, and that was absolutely cast iron proof that these were extraterrestrial.
And then a few years later, he got the Nobel, and he was the most courageous guy to go higher up in a hot air balloon.
In 1936, he got the Nobel Prize, and he shared it with Anderson, who discovered the positron.
Right, right. So that was the beginning of particle physics. It continued, as we know, with then particle accelerators, but cosmic rays are also being studied now much higher on the space station with a detector that was built at CERN, but that's Elisa's part. Before going to talk about this detector that she helped building and is now in space, we can talk about your special cosmic ray detector. It's called Cloud, and it's not by chance.
Yeah, it's, I mean, it's here. It's a few hundred meters away across the road at CERN. It's very strange for CERN because it's studying atmospheric science. Now, CERN doesn't do atmospheric science, but, or it didn't do atmospheric science, it does now, but it does do cosmic rays. I mean, the cosmic rays, as I'm sure you know, are part of the CERN Convention, the document, the Constitution, and cosmic rays are explicitly mentioned. About 30 years ago now, I listened to a lecture here across the road, and it presented some studies of some Danish scientists which seemed to show that clouds on Earth were varying with cosmic rays. And that just struck me as an incredibly interesting question. So that Christmas, while we were over at my sister-in-law's in Paris, they were out shopping, and I was thinking how we could do an experiment at CERN to really check whether this was real or not. And that's where Cloud was born. That was the easy part. The idea was the easy part. It took us 6 years to convince CERN why they should be doing atmospheric science. They finally gave up. It was a competition between me and CERN management, I think, for 6 years. They finally gave up, and we've been essentially in discovery mode since then.
So tell us more about Cloud. We can see various things here in a typical CERN experimental area. On the surface, it's on the surface, not underground. Maybe, we can maybe stay here. Or
so, I mean, what you see there is the outside of cloud. Inside, there's a chamber. And
which you can see on the left, right?
Actually, oh yes, that's a view inside. That starlit thing is a bird, is a fisheye view from the lower manhole. In simple terms, it's the cleanest box in the world. We're studying in the laboratory under controlled conditions the formation of aerosol particles which become cloud seeds. So every single cloud in the sky forms on an aerosol particle. And the majority, certainly in clean environments, of those particles are coming from very, very dilute trace vapors in the atmosphere, which are somehow what is called nucleating, forming a liquid cluster, which then grows, and when it exceeds a certain size, that will seed a cloud droplet. And these experiments are extremely difficult to do because those vapors are present in the atmosphere at extremely low concentrations, less than 1 in a trillion molecules. 1 in a trillion is 1 drop of water in 10 Olympic swimming pools. And we have to control the impurities in that chamber to 1% of that. And actually, it's the only chamber in the world that's managed to do it using CERN know-how, actually. And we've just had a ball for 15 years. Measuring all kinds of stuff.
And you had a lot of success, but as we can see from the next slide that is not coming, because your results were published in Nature, and you had a lot of even cover of Nature. There they are. Yes.
Yeah, I mean, this is a very interesting aspect of science that's repeated again and again. We designed the experiment to go after a certain question, and we're still addressing that. But we found, because it was in a totally new environment with a totally new technical capability, we've actually branched out into doing much more. Aerosol particles are extremely interesting to everybody in the audience, whether they know it or not. It affects human health. They drive the formation of smog in cities, but at the same time, they are very deeply implicated in climate change. So as well as the famous increasing greenhouse gases, human activities have increased other pollution, which has increased cloud cover, and that's actually offset part of the warming from the greenhouse gases. But all the uncertainty in climate models in projecting how much it's going to warm later this century under different scenarios is because we don't understand aerosols well enough. And clouds doing the sort of laboratory experiments, you could say, to constrain that in climate models.
It's giving a lot of contribution. It's changing a bit. This is an animation showing how it works. So you get real cosmic rays, or you get cosmic rays from accelerators?
No, I mean, the reason cloud is at CERN, apart from the trivial reason that was where I worked, is that we use a CERN particle beam as an adjustable artificial source of cosmic rays, and we shoot that through the chamber and see what the difference in the production of these particles is when the beam is present or when it's not present, or indeed when we put a big electric field and remove all the ions from the chamber. So the whole name of the game is these are controlled experiments where every single parameter in there, temperature, gases, everything, including cosmic ray intensity, is controlled.
We issued a press release last week about your latest result, which has to do with marine environment, which is extremely interesting, especially for tonight. We had a lot of sailors from Magellan to Justine Metro.
Yeah, I mean, before cloud started, it was thought that essentially all these seeds were forming in the atmosphere from sulfuric acid, and most sulfuric acid in the atmosphere is coming from anthropogenic sulfur dioxide, which is from sulfur burning in fossil fuels. What we've found, especially in cloud, is that there are some very, very important natural sources of aerosol particles. One of them is trees over the Amazon. When these vapors get to high altitude, they pop and make cloud seeds. But the latest one, the one that was reported last month in Nature, shows that phytoplankton are creatures that live, actually photosynthesize.
And it's the basis of the food chain. It's the very first bricks of the food chain.
And again, they are hugely underappreciated. Everybody should be interested in phytoplankton because 50 to 70% of the oxygen you're all breathing is coming from phytoplankton, not from trees, from phytoplankton. So they're not only create the lungs of the earth, I mean, an important part of the lungs of the earth, but they also are creating, in this particular case, a vapor called dimethyl sulfide, which is converted to an acid called methane sulfonic acid. And that is just as effective as sulfuric acid in cool marine environments for making particles. And this, I think, will answer a very big problem inside current climate models. They can't explain a lot of aerosol production in the top of the atmosphere or in the Southern Ocean. This stuff in the top of the atmosphere is over the Atlantic and Pacific. And I think this methane sulfonic acid can really account for that. So it's not been put in a model yet because we only discovered it or reported it a month ago. But it's going to change. It's going to have a big effect.
Into the climate change model.
Yeah.
Thank you for this voyage into the clouds and how they form and how cosmic radiation and particles have an effect in our nature and our life on this planet. I think we should, before moving to the next speaker and the next subject, they're all interconnected, but because we are the last session, you can ask questions now after each presentation, and we have an open-ended session, more or less, just before the football match at 11. So if there are questions in the audience for Jasper, please raise your hands, and that's the time to ask. I don't see very well, so yeah, maybe I need somebody's going around with microphone. Anyone? Yes, there's someone there. Please.
If phytoplankton is very important to everyone, can we grow it at home to help?
I'm sure you certainly can grow it at home, but you can't compete with the surface of the ocean. I mean, the ocean surface is 2/3 of the
planet.
Earth. There are huge phytoplankton blooms in various parts. They need cool water, they need nutrients, and so on. If you really want to increase phytoplankton, you should do research on what's stopping them spreading more. But
plastic is one.
Plastic.
Yes. Plastic pollution.
It's polluting them. Okay.
Plastic pollution has an impact on the basis of the marine food chain, which is the basis of our life. So stop using single-use plastic. This is my message. But okay, maybe one more, and then yes.
Thank you for the presentation. The research that you did on vapors, could that potentially help in controlling the environment? Like, would humans be able to create clouds, create weather patterns, or would you be able to make it rain?
This is about geoengineering.
Okay, so you've touched on a couple of things there. In terms of making rain, there are serious efforts, as you know, for cloud seeding, and they have mixed results. I mean, they work on the principle that there's lots of supercooled water, and if you force that to crystallize, to form ice, it will rain out. And if you get a cloud in just the right state, you can do that. But it's very hard to really use that really systematically and make it work. The other aspect that you were touching on there is a very serious area of study for a lot of climate scientists, and that is whether we can engineer the climate by adjusting clouds and radiation control. And I don't do research in that. I fully support the work that's being done, but I think it's very, very difficult and very controversial for at least two reasons. One is aerosols only live in the atmosphere about a week in the troposphere. So if a future American president, if he's the person or she's the person who's funding this research, suddenly decides that they don't want to do it anymore, there will be a very big shock on the climate very quickly over a period of weeks, or maybe a year if the work is engineering the stratosphere. The other thing is, it's going to be highly non-uniform. Some regions, presumably the US, where this work will be done, I'm just assuming, will be nice and cool. Other places will get hotter. Other places will get drier or wetter. So there will be knock-on effects, and every single anomaly in the climate will be put down as the responsibility of whoever's doing climate engineering. So it's hugely, hugely controversial, but I do support the research that's done.
Research is always good.
Yeah.
Thank you, Jasper. So our next speaker, on va parler en français avec Evelyne Beaumont. Evelyne, c'est la directrice du Centre de la vie dans l'univers, un centre récemment créé par l'Université de Genève. C'est une astrophysicienne. Et je pense que tout ça est parti d'un prix Nobel de physique que la ville de Genève a obtenu, la ville, 2 scientifiques genevois ont obtenu de l'Université de Genève. Raconte-nous cette histoire à partir d'un prix Nobel, c'est très intéressant.
Oui, alors du coup, effectivement, ces 2 personnes que vous voyez à l'écran, Michel Mayor et Didier Queloz, sont maintenant assez connus, et surtout en Suisse, pour la découverte de la première exoplanète. Donc une exoplanète, c'est une planète qui tourne autour d'une autre étoile que notre Soleil. Et donc avant cette découverte, on se doutait qu'il y en avait, mais on n'était pas vraiment sûr. Alors il y avait eu une autre découverte un petit peu plus tôt, en 92, mais dans un système très exotique. Et là, donc c'était en 95, la découverte de cette première exoplanète, et c'était, on verra, il y a une image un petit peu plus loin, mais c'était une étoile vraiment autour d'une étoile comme une planète, pardon, autour d'une étoile comme le Soleil. Et depuis cette première planète en 95, et ben aujourd'hui maintenant, c'est un chiffre qui date du 2 juillet, donc c'est tout récent. On a découvert plus de 6000 planètes, 6316 pour être exact. Et donc, on a remarqué que toutes ces planètes, elles étaient très diverses. Donc, on a des planètes comme Jupiter, on a des planètes aussi rocheuses comme la Terre, Mars, etc. Et on a aussi toute une classe de planètes qui sont un peu entre les deux, donc qui sont ce qu'on appelle des super-Terres ou des mini-Neptunes. Donc il faut vraiment imaginer des objets qui sont entre la Terre et Neptune en termes de taille. Les super-Terres, c'est plutôt des rocheuses plus grosses. Les mini-Neptunes, c'est comme Neptune, mais en plus petit. Et en fait, ce qui est vachement intéressant, c'est que ce type de planète n'existe pas dans d'autres systèmes solaires.
Ça, c'est Pégasi 51b, donc la première exoplanète qui a donné le prix Nobel à Michel Mayor et Didier Queloz.
Exactement.
Est-ce qu'elle ressemble à notre Terre?
Alors, pas du tout. Alors, si on devait la comparer à une planète, on la comparerait davantage à Jupiter, parce qu'elle fait à peu près la moitié de sa masse.
Elle est gazeuse aussi?
Elle est aussi gazeuse, mais la grosse différence, c'est qu'elle orbite autour de son étoile très, 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 très proche. Donc elle fait le tour de son étoile en quelques jours, alors que Jupiter, c'est plusieurs...
Et nous, on met 365 et quelques.
Exact. Ouais. Et donc cette planète, quand elle a été découverte, c'était un peu une surprise. Et d'ailleurs, ce qui a expliqué le fait que Michel Mayor et Didier Queloz ont un peu dû se battre contre la communauté pour faire accepter cette découverte. Parce qu'en fait, avant de découvrir cette planète, on pensait vraiment que les planètes comme Jupiter se trouvaient très loin de leur étoile, comme notre Jupiter à nous. Et donc, le fait de découvrir une planète comme Jupiter, mais si proche, c'était vraiment étonnant. Et donc, ils ont dû, essayer de changer un petit peu les idées. Et au final, ils ont réussi. Et grâce à eux, ça a lancé tout un domaine, le domaine de la recherche des exoplanètes. Et donc là, sur cette vidéo, je voulais un petit peu vous montrer où sont ces exoplanètes, parce que souvent...
Voilà, à quelle distance elles se trouvent?
Voilà, les distances. Donc là, vous voyez, on part de la Terre, vous voyez les constellations un petit peu en fond, et gardez un œil sur ces constellations, parce que vous allez voir à un moment qu'il y a des choses qui commencent à se passer. Donc là, on est en train de dézoomer, mais on est toujours dans notre système solaire. Donc vous allez voir, c'est assez long en fait de dézoomer jusqu'à ce qu'on trouve les premières étoiles. Donc là, vous voyez la comète Chury, vous voyez Jupiter justement dont on parlait tout à l'heure. Et donc là, on est encore dans le système solaire et on va dézoomer. Vous voyez, pour l'instant, il n'y a personne autour de nous. Et au bout d'un moment, vous allez commencer à voir nos premières voisines. Vous voyez Alpha du Centaure. À côté d'Alpha du Centaure, il y a Proxima du Centaure, qui est l'étoile la plus proche de notre système solaire. Et donc vous voyez les lignes là des constellations qui commencent. Les constellations sont maintenant toutes déformées parce que les étoiles ne sont pas dans le même plan. Et vous voyez aussi, peut-être, vous voyez, il y a des points verts et des points rouges. Et bien ça, c'est des étoiles autour desquelles on a découvert des planètes.
Incroyable.
Donc voilà notre environnement. Et donc la plupart des planètes qu'on a détectées sont quand même relativement proches de notre système solaire à cause des techniques de détection qu'on a. Alors vous voyez le long cône comme ça, rouge, ça c'est des planètes qui ont été découvertes avec un satellite américain qui s'appelait Kepler. Et vous voyez aussi qu'on a découvert des planètes très très loin, proches du centre de notre galaxie, mais que globalement, à cette échelle, on a quand même regardé qu'un minuscule, en fait, finalement, endroit autour de nous.
Donc on peut oublier d'avoir une deuxième Terre pour nous.
Alors, oui, parce que la plus proche, qui est Proxima du Centaure, elle est à 4,5 années-lumière.
Et on ne sait même pas si elle est habitable.
Alors, il y a une planète autour de cette étoile qui est dans la zone habitable, dont je parle un petit peu plus loin. Mais elle est la plus proche de nous, mais c'est encore très très loin. C'est des distances astronomiques, comme on dit. Et donc, si on devait y aller, ça nous prendrait énormément de temps, plusieurs générations, et on n'a pas du tout la technologie pour faire ça.
Donc votre centre, il s'appelle Centre de la vie dans l'univers. Donc, à part faire un catalogue de toutes les planètes extrasolaires, on est arrivé à 6000. Vous étudiez la possibilité de vie sur ces planètes.
Alors, voilà, et effectivement, mais avant de parler de possibilités de vie, on est intéressé par le climat de ces planètes, et c'est là que ça rebondit sur l'intervention précédente.
Il y a des nuages sur ces planètes ?
Alors, effectivement, il y a des nuages sur toutes les planètes, globalement. Et en fait, ici, cette représentation vous montre un petit peu ce qu'on essaie de faire. Donc, on a une exoplanète qu'on détecte autour d'une étoile, et on essaie de faire de la modélisation sur les climats potentiels que cette planète pourrait avoir. Et donc, du coup, on utilise un peu les mêmes genres de modèles qu'ils utilisent pour le GIEC, mais des modèles beaucoup plus simplifiés, où on enlève toutes les paramétrisations qui sont très spécifiques à la Terre, en particulier comment on crée les nuages, tout ça. Ici, on est beaucoup plus libre dans ce qu'on essaie de faire. Mais voilà, on peut donc modéliser ces planètes en 3D, avoir la température à la surface, la température dans l'atmosphère, s'il y a des vents, s'il y a des nuages, si oui, où ils sont, est-ce que ça a un effet sur la température en surface. Et ensuite, avec les conditions de surface en température, en pression, on est capable de dire de l'eau liquide peut survivre à la surface de cette planète. Et ça nous emmène au concept de la slide d'après, qui est justement le concept de la zone habitable, qui est, en gros, c'est assez simple à comprendre. C'est-à-dire que, par exemple, la Terre est dans la zone habitable du Soleil, heureusement pour nous. C'est pour ça qu'on a de l'eau, etc., sous forme liquide à la surface de notre planète.
C'est toute une question de distance de notre étoile.
Voilà, c'est une estimation basée sur la distance à l'étoile, effectivement. Et donc, en fait, c'est assez simple à comprendre dans le sens où si on est très proche de l'étoile, on va être trop chaud, et donc l'eau sera sous forme de vapeur dans l'atmosphère. Au contraire, si on est trop loin, il fait trop froid, et donc l'eau sera sous forme de glace. Mais donc, il y a cette fameuse zone habitable dans laquelle, si on met une planète avec la bonne atmosphère et de l'eau, l'eau pourrait potentiellement être liquide à sa surface.
Et donc, le liquide est un signe de possibilité de vie, c'est ça ?
Oui. Alors, j'aurais voulu juste parler juste des nuages avant de partir sur la vie, justement pour rebondir sur l'importance des nuages.
Oui.
Parce qu'en fait, on a montré que en fait, la limite interne de la zone habitable, pour des planètes qui tournent très très lentement sur elles-mêmes, en fait, dans des conditions comme ça, ce qui se passe, c'est qu'il y a un gros nuage qui se forme du côté jour de la planète et qui protège la planète de l'insolation de son étoile. Donc ça fait rebondir les rayons qui viennent de l'étoile. Et du coup, grâce à ce mécanisme basé sur les nuages, la planète peut garder des conditions habitables à sa surface plus longtemps. Donc
c'est fondamental, les nuages aussi pour les exoplanètes.
Exactement, ça nous intéresse vraiment beaucoup de connaître mieux les nuages aussi pour nous, parce que justement ça définit les zones de cette fameuse, les limites de cette fameuse zone habitable.
Et donc déjà, zone habitable, c'est déjà le premier paramètre pour dire peut-être il y a de la vie ou pas. Donc il y a des nuages, il y a de l'eau. Et la vie, vous la cherchez comment ? Comme SETI, comme contact, on envoie des messages et on attend la réponse dans 10 000 ans ?
Non, pas vraiment, non. donc en fait, effectivement, on se sert de cette zone habitable pour nous donner les cibles, en fait, les planètes entre guillemets intéressantes. Et une fois qu'on les a identifiées, l'idée, en fait, c'est de regarder la composition de l'atmosphère de ces planètes pour y détecter des signes de vie ou des biomarqueurs. Peut-être vous avez entendu parler de ce concept. Et en gros, qu'est-ce que ça veut dire? Ça veut dire s'il y a de la vie sur une planète et que cette vie est suffisamment développée, elle a pu modifier la composition chimique de son atmosphère.
Ah, d'accord.
Et c'est ce qui s'est passé pour la Terre. On a parlé de l'oxygène et le phytoplancton. J'ai une slide un peu plus loin. C'est peut-être celle d'après, je ne me souviens plus.
Voyons.
Oui, voilà. Donc pour la Terre, grâce à ces petits organismes-là qui sont des cyanobactéries, qui ont inventé, entre guillemets, la photosynthèse il y a plus de 3 milliards d'années, petit à petit, le métabolisme qui est basé sur la photosynthèse s'est un petit peu répandu dans tout le vivant. Et au bout d'un moment, on a vu la concentration en oxygène de notre propre planète augmenter jusqu'à obtenir les 20% qu'on a actuellement. Et donc sur Terre, la présence d'oxygène, finalement, est un biomarqueur.
Oui.
Si on devait tuer tous les phytoplanctons, tout ça, ce que je ne souhaite pas, petit à petit, la quantité d'oxygène va disparaître. Et donc, on pourrait se dire, détectons de l'oxygène dans les atmosphères des exoplanètes.
Et comment?
Et voilà, par exemple, avec le James Webb Space Telescope, alors il ne sera peut-être pas en capacité de le faire lui, mais je l'ai mis quand même parce que ça représentait une avancée technologique gigantesque dans la compréhension des atmosphères des exoplanètes, mais c'est plutôt des exoplanètes plus grosses et plus chaudes. Et pour ça, le James Webb, il est vraiment tip-top. Ouais. Et donc, on a pu détecter des molécules, du CO2, du méthane, la présence de nuages, la présence d'aérosols. Donc, ça a vraiment révolutionné pas mal notre science observationnelle sur les atmosphères des exoplanètes. Mais voilà, comme je disais, ça c'est vraiment encore, on va dire, les balbutiements, parce que le James Webb peut faire des grosses planètes chaudes, mais les petites planètes pas trop chaudes, tempérées, donc celles qui nous intéressent nous quand on parle de la vie dans l'univers, le James Webb va probablement pas réussir à dire grand-chose, parce que c'est très difficile, les atmosphères sont fines, c'est vraiment très difficile de détecter la composition de leurs atmosphères.
Est-ce que vous avez d'autres instruments en préparation qui peuvent vous aider dans cette quête?
Exactement, et donc là je vous ai mis une petite vidéo qui a été faite de l'Extremely Large Telescope, donc, qui est un télescope en construction au Chili. Donc c'est immense. Le miroir lui-même fait 39 mètres de diamètre. Je pense que ça rentre même pas dans la salle ou presque. Et donc lui, en particulier, va pouvoir en fait, a priori, sonder l'atmosphère de notre plus proche voisine. Donc je vous ai parlé de Proxima du Centaure tout à l'heure. Et on a parlé d'une planète dans la zone habitable Proxima du Centaure, donc elle s'appelle Proxima B. Et en fait, cette planète va être sondée avec ce télescope. Et donc, dans quelques années, a priori, l'instrument qui pourrait faire ça sera en fonctionnement en 2035. Donc en 2035, je pense qu'on espère qu'on aura du temps pour observer cette planète. Potentiellement, on pourra voir si elle a une atmosphère et si oui, de quoi elle est faite. Et ça, c'est la première étape avant de pouvoir détecter ces fameux biomarqueurs. Mais en fait, la difficulté avec les biomarqueurs, je vous ai donné l'exemple de l'oxygène, c'est que l'oxygène, ça marche bien pour la Terre, mais ça ne marche pas forcément bien pour cette planète-là. Et donc c'est là que toute la difficulté réside, et c'est pour ça que le Centre pour la vie dans l'univers a été créé en 2021, parce qu'en fait, pour savoir quoi chercher pour détecter la vie, il nous faut toutes les disciplines qu'on a essayé de mettre ensemble dans le centre. Donc
vous avez des biologistes, vous avez très interdisciplinaire.
C'est ça. Donc il faut de la chimie, de la géologie, des sciences du climat. J'ai dit quoi? Chimie, biologie, géologie, sciences du climat, et puis astrophysique pour essayer d'observer tout de loin.
Évidemment. Et voilà. Planétologie.
Et la planétologie en général, effectivement. Et donc c'est ce qu'on essaie de faire dans ce centre. Et on peut mettre la dernière slide, je pense, voilà. Et aussi, je voulais aussi mentionner qu'au niveau suisse, on a un gros projet qui vient de commencer. Donc en Suisse, on a ces gros projets de 12 ans qui s'appellent des NCCR. Et donc on a commencé récemment, si vous pouvez juste cliquer, le NCCR Genesis, qui en gros prend ce même principe de mettre toutes ces disciplines ensemble, mais là, cette fois, à l'échelle de la Suisse, avec des partenaires donc à Lausanne, à Zurich, à Fribourg, dans le Tessin, enfin, il y a un peu partout en Suisse, et on se met tous ensemble. Et donc voilà, on a 12 ans de recherche qui nous attendent pour voilà, trouver les bons biomarqueurs, pour voilà, essayer de comprendre comment les planètes restent habitables aussi sur des échelles de temps géologiques. Et donc, on va essayer de faire tout ça en 12 ans.
Félicitations pour ce magnifique voyage jusqu'à Proxima Centauri et Proxima Centauri B. Et je pense qu'on peut prendre des questions. We can also ask questions in English because Emeline understands English perfectly, like every scientist. So please raise your hands if you want to know anything from Emeline and life in other planets. There's a hand there.
Thank you very much for the excellent presentation. I would like to understand how the upcoming European Space Agency mission of Plato could augment our understanding of exoplanets.
Can you repeat the what?
Plato, the new mission, I think that is coming up. How does it complement the ELT observations?
Okay, so Plato is not going to characterize the atmospheres, so try to estimate the chemical composition of the atmospheres, but it's going to detect new planets. And one of the aim of Plato is actually to try to detect an Earth-like planet around a Sun-like star. So basically, all the planets that are interesting for me, so the small rocky planets in the habitable zone of the star, most of them have been detected around very low mass stars. So those stars are very different from our sun. But if you talk about habitability, one strategy is to say, okay, let's try to find the planet which is as close as possible to the Earth. So a rocky planet about the size, mass of the Earth around a star which is like the sun. And so Plato is going to try to do that. And then we will have future missions which I didn't mention here, like for instance the Habitable World Observatory or the Life Interferometer that will be able to look at the atmospheres of these planets. So hopefully Plato will discover them, and then we will have this next generation of instruments, but it's 2040, 50, so we have to be patient.
Any other raised hands? Any other curiosity? One more here. Thank you.
Des raisons de penser que les planètes rocheuses sont moins, ont des environnements moins favorables à l'apparition de la vie que les planètes gazeuses. Et si ce n'est pas le cas, est-ce qu'on ne peut pas aussi regarder les atmosphères des planètes comme des planètes gazeuses avec James Webb?
Alors c'est une très bonne question. Une des raisons pour ça, c'est parce qu'en fait on pense que quand on se pose la question de l'origine de la vie, on pense qu'en fait que les interactions entre l'eau liquide et les minéraux sont très importantes. Parce que ça facilite certaines réactions chimiques, ça apporte des éléments qu'on ne trouve pas d'habitude dans les atmosphères. Et que du coup, dans ce cadre-là, on est plutôt intéressé à plutôt des rocheuses, justement, parce qu'on a besoin de ce contact entre l'eau et le monde minéral. Mais après, je voulais quand même juste dire que il y a des gens qui sont intéressés par ça, parce qu'en fait, on pourrait imaginer des formes de vie qui vivent justement dans les atmosphères. Alors, des fois, on parle aussi de Vénus, mais les atmosphères de géantes gazeuses, parce qu'il y a forcément des petites gouttes d'eau en suspension. Mais alors, c'est pas impossible, mais ça paraît peu probable dans le sens où comment cette vie-là, elle a pu apparaître, ça paraît plus difficile à expliquer. Mais bon, en même temps, comme on en sait tellement peu sur l'apparition de la vie sur Terre, peut-être qu'il faudrait effectivement pas trop se limiter. Mais là, en ce moment, on a plutôt une approche pragmatique à essayer de dire, OK, on va essayer de trouver des habitats le plus semblables à la Terre, et on part de là. Ouais.
Thank you, Emeline. We have to keep going with the program. Thank you very much. And we stay in space We stay in space with our next guest, Elisa Laudi. Elisa is an engineer. She's currently working for the ALICE detector in the technical coordination. ALICE is a detector which is under the Earth in Saint-Genis, between Saint-Genis and Cergy, for those from the region, 100 meters below ground, and it does quark gluon plasma. But today, we're here to talk about your start, the start of your career with a very special detector that brought you around the world to Kennedy Space Center and also to CERN. But before I ask you questions, I want to show you something that you experienced with me.
It's T-9 and counting. This is the real final countdown for Space Shuttle Endeavour, as mission management team has just given the final go for launch. In less than 9 minutes, Endeavour will lift off from pad 39A with its precious cargo, the Alpha Magnetic Spectrometer, AMS. So all I've left to say is go Endeavour, go AMS.
So Elisa, do you remember this day?
Of course, yes. I remember very well these days. Yes, I was watching as you the launch from Cape Canaveral after 4 or 5 years working in AMS, as I started for my PhD on the tracker thermal control system of AMS first, and then let's say my responsibility enlarged until up to the mechanical integration team. I was part of the CERN mechanical integration team interfacing with NASA. That's why then finally I was there seeing the launch.
And I have another surprise for you, because the day after, we were there with you a few years ago.
Banana Creek is always inside KSC. It was a very good spot anyway. But of course, yeah, there were the clouds, so we couldn't see completely all the launch, but it was beautiful and wonderful anyway.
So what's the next step now?
For me, the next step is in Houston. We will be there in the flight day 4 to see the transfer of AMS to the International Space Station, and then check some thermal data, and after that, a new project.
So with you was Corrado Gargiulo, who was your colleague and engineer also. Isn't it great to see a young engineer at Kennedy Space Center watching the launch, and the day after, okay, I'm going to Houston?
So young compared to now. Yes, no, because let's say I was going also to Houston just to see the transfer, so the mechanical part, but as I was part also the thermal engineering team, as my PhD was more on the thermal part, I installed all the thermal sensors, so these thermocouple and things that were helping all the engineer to keep track of the thermal environment AMS, and so that's why I spent also a month in Houston as responsible, let's say, of this station. And then, yeah, the new project, staying in the space business. I have been working in a company for 2 years as an assembly integration engineer. So proud and with all the knowledge that I had from the responsible of our integration team, Corrado Gargiulo. And after a couple of years, I saw a position opening at CERN for working on the tracker control system and in the cooling of ALICE. So again, mechanical integration, cooling system, and exactly of the tracker. So the same as I started in AMS. And that's how I came back finally to CERN.
So this is what happens to you when you get a PhD in engineering. This is for the young people. So we have an exceptional guest right now who had a crucial role in that space shuttle that you saw. And I hope we have a Zoom from Houston. He's here with us tonight, Roberto Vittori. Roberto, can you hear me? Are you there?
I can hear you loud and clear. Can you hear me?
Yes, and we can also see you very well. Thank you for joining us on this stage. We just seen you. You were in that shuttle that we just saw flying off a few years ago. So what were the highlights, Roberto, of the AMS adventure?
So I just saw the images when we finally reached countdown to 0 and lift off. That was incredible. You probably seen from the image there was a cloud coverage. And with clouds, you don't take off with the shuttle. So we were waiting. The fear was another delay. But at the very last moment, there was a small opening in the cloud, big enough for us to lift off. It was absolutely incredible. And I still remember, as it was now, there was an eagle flying right on top of us. Wow. And yeah, he moved on the side at the time we start to...
So you didn't kill it?
No, we didn't kill it. It just fly by.
That's amazing. We should be seeing some images. You had a very, very important role when you got to the station with this big object in the cargo bay of Space Shuttle Endeavour. And your job was to install AMS, a unique payload that just got inside, that we are seeing it, and transfer it from the cargo bay of Endeavour to the station with a robotic arm. We are seeing this operation right now. And I'm just thinking of you in that moment. Were you sweating? Wasn't it very difficult for somebody? It was not your object. It belonged to a collaboration of physicists worldwide. What were the difficulties of this operation, especially from the emotional point of view?
So that was just shortly after we docked to the International Space Station, shortly after we got to space. And when you arrive in space, you have to adapt to microgravity. So it's not the easiest moment to do anything, and especially to do a very precise task as necessary for the robotic arm to lift off the IMS. And it was a big question mark how everything was going to perform. During launch, the shuttle has a characteristic. There are huge amount of vibrations. So the concern was that something may have shifted. The tolerances for the lifting of the IMS out of the bay were centimeters, even smaller. So the question was how everything was going to happen. But the shuttle arm performed extremely well, very smooth, and that was an incredible experience. Everything went very, very smoothly. First time ever that there was a shake hand, so-called shake hand. It was not a shaking hand, but shuttle arm took the payload IMS off the bay, and then the station arm took it to install it on the truss.
So there were two of you working, one in the station, of course, and you in the shuttle, right?
Yeah, it was myself operating the robotic arm of the shuttle, and Gregory Johnson, nicknamed Box, our pilot, on the station side, and he was operating the station robotic arm.
Incredible. So I think you met Elisa for sure. She was part of the AMS collaboration. She's here with us, and I'm sure she has a question for you.
Ciao, Roberto. Yes, we have met several times during the years, during the preparation. Yeah, I was wondering, the installation of AMS was quite a coordination from the astronaut and the ground team, where AMS was part of. What was special? What was what the AMS collaboration brought you, and you thought that was easy for your job? Let's say, how did we make easier your job and this transfer of AMS?
Yeah, Elisa, nice seeing you after so many years. In fact, it was almost exactly 15 years ago. Oh, by the way, today is what is the 10th of July, maybe. Yeah, it was. That's a small parenthesis. STS-135, after 134-hour mission, was in space as we speak, 15 years ago. So AMS in a very remarkable. It is a very remarkable experiment. It's more than a payload. It's a part of the history of the International Space Station. It's part of history of a human space flight and science in space. And the team was incredible. The complexity of IMS, the capability of the team to manage not only the complexity of IMS, but the complexity of IMS in the context of the complexity of the shuttle program at this very last flight in the context of ISS reaching station complete. So IMS is the converging point of three main elements. IMS itself, science, shuttle program getting to the end, ISS getting to station complete. And the IMS team was incredible, capable to navigate throughout the complexity of a world that were parallel, and it was an incredible positive experience. And oh, by the way, as we speak, we are in 2025, IMS is thinking to get upgraded.
Exactly. Yes,
That is incredible appropriate because, you know, we hope to be on the moon soon, but unfortunately, life is never easy. There are ups and downs. Probably the station will not retire in 2030, probably will not get to the moon anytime soon. So IMS is becoming the real actor of the next future with this upgrade and with the science that is continuing to offering us.
So Roberto, I have a surprise for you. We have a successor, in a way, of your generation of astronauts. We have here with us Megan Christian, who has been selected in the Reserve Corps of the European Space Agency at the latest selections. Megan, I'm sure you have a question for Roberto. Sorry for getting you back on stage.
Ciao Roberto. I have many questions, but I will limit myself to one. So you were flying at a time, a really golden sort of time of space exploration, you know, with the space shuttle and the heading towards completion of the ISS. But then you saw kind of the end of the space shuttle program and the uncertainty that there was around that. So what recommendations do you have for those of us now that are heading towards the end of the space station?
Well, Megan, nice talking to you. I don't think we have ever met. Hopefully we'll meet in the future. So I believe retirement of the space shuttle was a mistake, was a big mistake done by the US. This was unnecessary, it was premature. I know, 1st of February 2003, tragic accident. Shuttle was an experimental machine. The shuttle did not deserve to retire. Now, what comes next? What comes next is very interesting, very promising, but somewhat confused. Especially because Crew Dragon, yes, it has the same strength of the Soyuz. The Soyuz has been reliably flying for 60 years plus. Crew Dragon should be the same. Unfortunately, we are now somehow concentrating on something that it's not very likely that we'll see a future, that is the Starship. Starship could for sure be a very incredibly efficient and economic transportation for cargo, not for humans. Power landings doesn't seem to be capable to bring astronauts anytime soon. So my hope for the new generation of astronauts is to have a SpaceX equivalent, but concentrating on the only possible evolution that can bring fully reusable systems, that is evolution of aircraft into spacecraft. So the idea of Virgin Galactic, well, yeah, they are kind of focusing on space tourism, and that is not going to be the future, but the idea itself is the correct idea. So what I hope for the future of human space flight is that we will go through this bubble, like SpaceX IPO, that's a huge bubble, it's a concern, go through that and find again the time and resources to continue flying space with capsule like Soyuz and Crew Dragon, and fly back to orbit and land to landings, to whatever will be coming after the shuttle, that obviously we don't have anything yet, but hopefully will come back soon.
Thank you, Roberto. Thank you, Megan, for this question. I'm sure there are questions in the audience. We can take just a couple. Please, loud and clear, if you can, put the microphone near your mouth. It's coming. the auditorium is very big.
It's a very pleasure to talk with you. I'm Italian, and I remember you several times in the Italian TV, especially with the journalist Piero Angela. I want to ask you, of course, for me, astronauts are still, let's say, the heroes of the heroes that you think about when you are a boy, no? What is the most difficult part and the most, let's say, terrifying feeling that you feel when you go up there in the space? And what is the feeling that you miss so much now when you think about those flights that you did? Thank you.
Well, thank you for the question. Obviously, flying space is very special, from liftoff until you reach microgravity. When you look down from the ISS or shuttle or Soyuz to the planet, is an incredible three-dimensional view down to the beautifulness of the planet. And then the re-entry and landing, that is probably the most intense part of the entire journey. The re-entry, especially with the Soyuz, is as close as you can be to die without dying. It's almost an out-of-control situation in which the combination of yourself being weak because of the microgravity plus dehydration plus the trajectory of the Soyuz itself that is not controlled, is partially stabilized during re-entry. The event one after the other until what they call soft touchdown, Myatka Posадки in Russian, that means soft touchdown, but there is nothing soft for the touchdown. It's as close as you can experience a crash with an aircraft without in reality crashing. For the rest, flying space is unique. Our future of mankind is in space. I don't believe that it's possible to correlate space with pleasure. People talk about space tourism. I don't think it's going to happen. At best, it's an extreme sport, flying space. And my way to say is that one step after the other, going to the future, as for sure will be in space. The only sustainable way to continue to increase the global economy without destroying the Earth ecosystem is by using the extra atmospheric resources. So we need space. We need space for ourselves, for the planet, and for the future generations.
Thank you very much, Roberto. Let's make a big applause. Thank you for your time. And I hope to meet you soon again here at CERN. You're always welcome. Thank you.
Bye-bye.
Bye, bye-bye. Okay, so just a little pause about AMS. You, the physicist, you can tell us what AMS is doing, completely different from cloud, but it's still working with cosmic rays, right?
Yeah, well, first of all, I should point out that I'm not on the AMS team.
Yes.
But I know Sam Ting very well. I know...
And he trusts you.
Many of the physicists. Sam doesn't trust anyone.
I know that.
He certainly doesn't trust me. But it really is a fantastic team of scientists. I think there isn't any, and I say this with no exaggeration, I don't think there's anybody else but Sam who could have brought this project off to such a success. It's his success, it's the success of the team, it's the astronaut success, it's NASA's success, but it's hugely complex and it's been very, very successful. What AMS is essentially a particle physics detector with a magnetic field flown up in space. It's just as complex, but it's obviously slightly more compact than any of the things attached to the LHC. The ability, the presence of the magnet is extremely important because it can detect positive and negative particles, and that means that's led to one of its most important discoveries. What it's amassed over these last 15 or so years is about 200 billion events. And
which means cosmic particles identified.
Cosmic rays. These experiments have to be done out in space. because as soon as the cosmic ray hits the upper atmosphere, it's destroyed and makes secondary particles. So it's impossible to do this experiment down on Earth or on top of a mountain. So it has to be done on space. This is by far the most sophisticated particle physics experiment in space. They're measuring processes to 100 times higher precision that have ever been meant before. And what this,
brings us.
There are two basic frontiers in particle physics. There's the high energy frontier that the LHC and its progeny are looking at, but there's also the high precision frontier. AMS is at the very high precision frontier, and those high precision measurements are challenging theories of the cosmos and where particles come from and so on. Now, having said that, when you take an advanced detector like AMS and you put it in a unique environment like space, you can expect discoveries. And by far, I think, the most intriguing discovery, which isn't explained, is the excess of positrons, anti-electrons, that has been found. Antimatter is very rare in the universe. It should, shortly after the Big Bang, there was equal amounts of matter and antimatter, and that should have annihilated and basically left pure energy. Here. But there was a little asymmetry somehow, and we wouldn't be here discussing it if it weren't for that asymmetry. So thank you for that asymmetry. That gives us
And that's what AMS is also studying.
And the AMS has looking at these antiparticles, it's found this unique signature of high energy anti-electrons, which are positrons, and the current favorite explanation of those, which there are other explanations, is that it could be dark matter annihilating two dark matter particles and making these very high energy positron anti-electron pairs. So who knows what it is, but it's giving huge amounts of very challenging data for cosmologists and particle physicists to figure out.
Thank you. I think we can go back to Houston right now if we have our next guest. Yes, is that I can announce who our next guest will be. He's another astronaut of the European Space Agency. He was a colonel of the Italian Air Force and test pilot with 2,000 flight hours on around 20 different military aircraft. And he completed 2 long-duration missions on the International Space Station. There we are. We can see Luca Skywalker. That's the name you deserved after your EVAs, your extravehicular activities. There's a big applause for you, Luca, from this room. Thank you for your time. So you are very connected to AMS because you did 4 spectacular spacewalks for the AMS upgrade. It was a major technical and also scientific operation in orbit. But last but not least, everybody knows here in the room that you were selected less than a month ago to be the pilot for the next Artemis mission that is very close to the moon exploration. Thank you for being with us, Luca.
Of course, thank you for having me. And I've been following the conversation about AMS. It brought back a lot of memories. And just a clarification, I still am in the Italian Air Force, still am in active duty.
Ah, okay, very good. Yes, so you're sharing your time between the two. So before we talk about the moon and your next adventure, I just wanted to ask you, during these 4 spacewalks for AMS, there were a few cliffhanger moments during that work. Can you tell us something about this crazy emotional moment?
Oh, yeah. And like you said, it was emotional. The first 3 EVAs went really well. Everything was smooth, and the operation between the astronauts and the ground and the engineering team, it was fantastic. And we were ahead of the timeline every time, so we really felt that everything was going well and that we could complete our job and close it up and start AMS until we went out on the last EVA, and that's when we went to check on all the components and the swaging that I had done on the previous EVA. The swaging, for those of you who are not familiar, is when you join 2 components and it has to be obviously an airtight and leak-proof environment so that you don't lose the cooling system, which was part of the original problem. We had just installed a new pump composed of 24 pumps with a reservoir of carbon dioxide as a cooling system. And because I had joined manually the old pipes with the new pipes, we had to make sure that none of those joints, and I made 8 of those, we had to make sure that none of them were leaking. On the very first one that I checked was leaking. And I mean, it was a big hit, because now I'm thinking, this is the last one that I made, and it's the first one that I'm checking. What's going to happen? How many of these are leaking, and was it something I did? So we went ahead, Drew and I, my other EV crew member. We went and checked the other 7, and none of them were leaking. The first one that I checked, number 5, was the only one that was leaking. And so we went per procedure where I torqued it down a little bit. That was the initial step. And then we had a 1-hour wait time to see if it was still leaking after we torqued it down. And it was a cliffhanger, because all this time we were checking, making sure that everything was going well, and we did not know what was happening in that joint. And so after about an hour, I went back, I opened up the system, I looked at the system, and it was still leaking, and my heart sank. I mean, I thought I had to go back and maybe cut the tube from 2 sides, make 2 more swaging, and then we were going to have to test it again, and we would have to, we were never going to be able to finish the job and start up AMS, which was the entire part of the job. But from the ground, I got a different instruction. They told me, hey, if it's broken, you cannot break it more. So how about you torque it some more? So I took out the, which is basically, it's a tool that every dad in the world has in their garage. It's a 10 wrench, and I just torqued it a little bit more. And then they sent me back to the airlock to grab everything just in case it didn't work, so that I could cut it up and make a jumper. But in the meantime, they said, we can just wait 45 minutes for this leak, because if it's still leaking, it will show up. So I went as fast as I could back to the airlock. I took all the equipment to make another repair. I went back as fast as I could, and then when the 45 minutes time stamp came by, I opened up the system one more time and I checked for leaks, and my heart jumped because it wasn't leaking. It didn't show any leak, and so I was ready to celebrate right there. If I had a bottle of champagne or prosecco,
you would have opened it.
I would have popped it right there.
Yeah, we are seeing the images of you doing this operation. I remember I was following from the AMS control room, and it was even Sam Ting, who never shows his emotion. He had a big smile on his face when you said that he was no longer red. That was really amazing. So lots of emotions in your job. I think another very emotional moment happened very recently on June 9. Can you describe what you felt and the mission ahead?
Yeah, you could say that it was a big emotion. As it happens, it was absolutely not on my horizon.
We don't believe you.
Oh, you should. And
no, I'm joking.
I will tell you why. You know that European flights are connected to specific contributions to our program. And so we expected, as European astronauts, to have 3 flights connected to the Gateway system. We have been working on it. I personally had been working on IHAB for several years. I was looking forward to it being launched and inserting around the moon. And then in February, during the ignition presentation by NASA, that program was put on the back burner, completely shutting down any option for flights, for immediate flights, for the time being. So together with the other European astronauts, I was just standing by to see what would happen and when we would have possibilities for new flights based on the new program that was presented. And so it was really there was no expectation to fly on any of the early flights until I got the phone call that my name had been put into the system for a pilot slot in Artemis 3. And I can tell you that something really rare happened. I was speechless.
Wow. Well, you had a lot of reason to do so, I think. I think you deserve another big applause for being so human and in spite of your skills, in spite of your exceptional skills. With us, there is Elisa Laudi, who was an engineer during the AMS construction, and that you met also. She has a question for you.
Yes, I was wondering for the... Ciao, Luca. I know that it was quite a complex operation, the one that you did for cutting my tubes, of course, but in general, the complexity of all the EVAs that you did. What of this complexity, what are the lessons learned that we are going to reuse for you, this Artemis mission?
So the specifics of a task like a spacewalk to repair AMS never go to waste. It requires competencies that expand from talking to a team of scientists and engineers to understand what you're going to perform and why. And even though I would probably not be performing spacewalks on Artemis 3, I did acquire a lot of confidence in the system, in how the system works when I plan a mission together with the flight director, the flight controllers, the crew that is assigned together with me to the mission. I am very, very, very aware, I'm extremely aware that by myself and my skills will never be sufficient, and I have to rely on other people's skills and capabilities to accomplish the mission. Those are not skills that you are born with. You learn those skills. You, as a human, you learn growing up to rely on yourself. And then when you have to achieve certain passages in your life and your career, you learn to rely on other people's skills and to trust the system, to trust how they work and how they prep the system for you to be able to accomplish your little part. You understand that you're just a small part of a bigger system. That skill is actually very important, and it will be indispensable in Artemis 3 because we are developing a mission that is currently being designed. We don't have, we right now don't have the spacecraft that we're working with, that we'll be working with. We actually don't even have the system that I will be flying with because Artemis 3 is currently being built. And I have to rely on the skills of the engineering team, the FIDOs, meaning those that design the trajectories, those that design the system that will allow me to rejoin and berth with the other spacecraft. For those systems to be working so that I can just perform my part as an operator. And I'm very grateful to be part of that team because it's a constant flow of information from one side to the other, the operators to the team and the team to the operators, so that we can design this system to be better and to be good enough for the next mission to have a better chance to complete their mission. That next mission is always more important.
We have a question from a younger colleague of yours who was just selected at the latest ESA astronaut selection in the Reserve Corps. It's Megan Christian. I don't know if you ever met, actually.
Many times, yes.
Yes, wonderful. So Megan is here with us, and she has a question for you.
It's great to see you there on the big screen, Luca. So the ISS has had a continuous human presence since the year 2000, but it was originally only supposed to have a 15-year lifespan, and we're coming, we're past that. At some point, it will have to have an end. And for me, that's incredibly emotional. But for you, who have lived on the station, it's been your home for a year or so, that must be even more emotional. So how does that make you feel? And then maybe the Artemis missions bring in an element of hope for the future that change those feelings a little bit. I'm just curious to hear.
I would say that both of those things that you said are true. Let's start with Artemis. I believe that this generation, your generation, will have a lot of work to do with the Artemis architecture. We are literally laying down just the basis for the entire operation to become more and more usable in the future. And you're young enough that you will see the results of our work being done right now. So there is a lot of hope. I think that the idea is that we will need a lot of astronauts if the plan to keep up the flights and to increase the number of flights to the moon actually gets applied, which I hope so. I hope so for everybody's sake. In terms of the International Space Station, we have had that sensation many times before. I'll tell you that every time you have a spacecraft that comes up, a cargo spacecraft, there are people that have worked on those spacecraft for years to build it, to make it workable, to pack it, to send it to the space station. And then we capture it, we use it, and then we take it down and we destroy it. I believe that a little bit of the work that's being put into those systems, it takes a little bit of the souls of the people that work in it. And the space station is amazing in that it's such an incredible construction, such an accomplishment for humanity that it carries a lot of soul. All those who have worked with it, all of those that have lived in it, commended it, made it their home, their safe place, their safe haven. It will take a lot of emotion to see it disappear when we deorbit it. But at the same time, it's the history of humanity. Everything, even incredible projects, they start, they grow, and then they come to an end. And that end needs to be the beginning of the next story. It's not the done deal. It's not, hey, we have been there, done that, now we are done. It's the beginning of the next evolution. We have used the space station well beyond the initial plan because it worked so well, because we learned so much from it. Just like AMS, we thought it was going to last 5 years, and then here we are, many years later, still getting incredible data. And I imagine that it will win a Nobel Prize one day, and make the space station program may well win a Nobel Prize. And when it finally is time to say goodbye to the space station, I think it will be okay to shed a couple of tears, a few tears, because a lot of people that have worked on that program will be looking at the end of it. But at the same time, it will be worth. I would say it will be worth celebrating the incredible accomplishment and its legacy. I would like to quote one of my crewmates, Drew Morgan, who was out with me during the AMS EVAs. He believes that the legacy of the space station goes well beyond the science, the exploration, the technology, the testing. It's a story of collaboration, cooperation that for the first time in history bridged gaps that were unimaginably big to overcome at the beginning. And that legacy still lives today, and we see it when we go to any newsrooms. The ISS is still the one place where we can live on the ground differences, legacies, and backgrounds and histories, and we can just focus on what humanity can do at its best.
These are fabulous words. Thank you very much, Luca. I'm sure there are questions from the audience. If you have a few more minutes, we cannot let you go without the audience being given the option of asking you a question. So there are many hands raised. I don't know if you can satisfy everyone, but there's a microphone going around.
Hello. Yeah. Hi. Hi, Luca. Thank you very much. Always very nice to hear you speak. My question is about the recent times. We saw you already in the simulator, in the Orion simulator. So I was wondering, what are your first impressions, what you can tell us? And yeah, thank you very much. Such an inspiration. And yeah, in bocca al lupo. Thank you.
Well, viva il lupo. Now you got me excited because I just started this, and yesterday was my first long sim. I spent 6 hours inside the cockpit working as the pilot, and the first impression is that it's about a generation and a half difference between the last Soyuz vehicle that I flew and going into this one. I have a lot of work to do to learn the systems. It's a wonderfully complex machine, and it should be. At the same time, I love the challenge of having not a whole lot of time to make this machine fly as if it was an extension of myself. So what I can tell you is that it looks like a very capable machine. Again, wonderfully complex with a lot of capability. I'm definitely glad that I have an experienced crew with me, because Dre Douglas, he has spent 2 years training for it, and Comrade, my commander, he has spent 20 years designing it. So I'm really glad to have their support. And this time I can only say that I will do my best to catch up as fast as I can, because I don't have a whole lot of time before I have to be very proficient flying it, controlling it, and acquiring my piloting skills, very, very fine piloting skills in order to perform the close proximity operations that we will need in order to rejoin, dock, undock with the future landers, and make sure that those procedures are well developed for the next spacecrafts.
Thank you. There's one more question here. We don't have a lot of time left, but please, let's take at least those who raised their hands.
Hi, Luca. Thank you for your time. You are truly an inspiration. So my question is, how do you face challenges during an EVA? And what does this teach us for the upcoming missions? And also, one last thing, what are you excited most for the upcoming work? Thank you.
Okay, I will answer the last question first. I don't rank anything. I just don't. And why would I? Why would I tell you I'm most excited about the launch and the millions of pounds of power of the rocket versus getting to orbit, versus the chance of designing the maneuvers to dock with 2 different spacecraft and for the first time? Why would I rank those things? I don't. I'm looking forward to all those things because that's the beauty of my job. Even though we astronauts are very ordinary people, the job is extraordinary. I can guarantee that. And in terms of challenges during an EVA versus a mission where you don't have EVAs, I would say that it's the way I take on the challenge is as a blank page. I go in without any expectations, and I let the training, my skills, the flow, the people that train me, I let them fill that page with everything that I will need in order to perform and to overcome a challenge. I am very, very basic as a human. I need to learn skills like everybody else. And so when I go into a new challenge, I go in as an open blank page, and then I let my experience together with everybody else slowly fill it in.
Wonderful. One last question. Don't fight, but I let the person with the microphone decide where to go.
Hi, Luca. Thank you for talking to us today. My question's about Europe's future with these kind of missions. As you mentioned, the amount of European astronauts that take part is dependent on the contributions made by ESA. And in ESA's most recent ministerial, we put a record number of finance into defense and security, and most countries massively reduce their contributions to exploration. My question is how this is going to affect European contributions in these kind of exploration missions, which are, for what I see, the most exciting things for us. But how's that going to affect us?
Well, thank you for that. Incredibly enough, what you're talking about happened about 9 months ago. It was in Bremen at the last Ministerial Council, and it was a different world. It was 6 months ago, 7 months ago, and it was a different world because we had a program where ESA had already a massive contribution to the architecture of Artemis, and then it all changed. And it's still a very volatile world where a lot of things keep changing. I believe that ESA has currently the right approach. We are preparing several steps this year to come up with a plan for Europe to become more independent in terms of access to space and our capability to explore and develop technology and prep and prepare our own exploration plans. I believe that because there is a saying that it would be a sin not to take advantage of a crisis. And because there is a crisis, I would say, I think that the approach to take advantage of it, showing that we need to become, as Europeans, more evolved in the fields of space flight, human space flight and exploration. I believe that there's a momentum that the countries understand. And so I would say that our plan to provide a path to space flight independence is the correct one, and it's exciting. I share your view that human space flight and exploration is probably the most exciting part of space flight. Although I would say that the robotic side can be just as inspiring when I think back of some of the things that we did, like landing on a comet. But in general, if I look at the enthusiasm that we saw in Bremen when we exceeded our expectations of financing by the countries, I would say that I can imagine that same level of enthusiasm going into the next step, the intermediate ministerial that we will have later this year. It's a whole project that will start in Toulouse with the summit, with the Space Summit, where we will present as ESA what our projects are. And hopefully my enthusiasm, your enthusiasm will be shared by the decision makers, and we can look forward to a development and to a better Europe.
I think it's time to stop with this message of hope. Thank you enormously, Luca, for your time. It's a busy time. You're training all day. It must be tiring. It's exciting, but it must be tiring. Thank you for letting us fly with you, and we hope to see you flying very soon. We will all be there, I'm definitely sure. Thanks to the audience, thanks to our speakers, Jasper Kirkby, Emmeline Beaumont, Elisa Laudi, and Megan. Christian, thank you for coming back on stage. Thank you, bye-bye. The party goes on outside with more music, food and drinks, and in 1 hour, the football match, England against Norway. Thank you, everyone.